Look who's back. It's me. I'm going to learn about Quintic stuff today. So, this is the quest for the Quintic. Um, so far, summary of the quest so far. Previously on Quest for the Quintic, we understood some ring theory on Monday and it was really good. We learned loads of stuff about different sorts of rings, made a lovely table, felt very accomplished. Tuesday, we did a forced march through all of the Galois theory notes, until we got to the Quintic, but didn't understand anything. Wednesday, we went back and really struggled to understand some group theory because we saw some group theory turn up near the end, and we really tried to get to grips with the field extensions. And today we're going to look at those special sorts of field extensions. We got to yesterday just this kind of sense of the fundamental theorem of Galois extensions, which is something to do with normal subgroups. We're going to have a look at section 5 of the notes today. Head out there, see what we can find. I remember section 5 being very, very difficult, so today is going to be one of those difficult days. Like Tuesday was pretty tough. Wednesday was also a lot of bits and pieces. So I've skipped over theorem of the primitive element. It's sort of fine. It uses a lot. It's sort of fine, I think. In here, I've also skipped, so getting through to section 5, which is what I want to do today. Here's where we were yesterday, fundamental theorem of Galois theory, which is so fun to say. Something about subgroups, and the small, so you've got an intermediate field M, and then M over K is a Galois extension, if and only if that group, kind of subgroup. The subgroup is a normal subgroup of that's a normal subgroup of the overall Galois group. Something like that. Cool. I paused a lot there while I was trying to remember where GM lives. I'm still being thrown by the notation in this section only, where GM is shorthand for Galois LM. I'm considering at some point just going through and rewriting this. It's like, to make it look nicer. Well, nicer in my opinion. So this one is L over M. That's all by definition. That's cheeky. Which is then Tower law stuff to say that that's M over K. Yeah, okay, really quickly looking at this one more time so it's in my head. There's a lot of Arthur's lemma stuff going on to talk about which bits are fixed, and that there's this correspondence with the subgroups and the field that's fixed. Yeah, via this sort of idea. That's the field that's fixed by, that's the stuff that's fixed by H. Over there you get a finite Galois extension. Arthur's lemma, still want to understand the proof, still want to go back and look at it, but that's what we had. Consequence of 3.17. 3.17 was just counting the size of a Galois extension. So if this is a Galois extension, then that's the size because of how it's defined. That's L over M for this one. It's just annoying. It doesn't have any L's in it. How am I going to remember that that means the Galois group of L over M as an extension? Oh well. There's some homomorphism stuff to go down here and talking about M being fixed. And this took me ages to think about yesterday. I have a question mark. So we're talking about this is the way around where GM is a normal subgroup. And then just from definitions, the subgroup for Okay, so that would be the subgroup for, yeah, this. There it is on the right. The subgroup of the overall Galois group that fixes gamma m is just the same thing, and it's a bijection. For each subgroup there's a subfield, so those are the same subfield. I think I need to understand the bijection, and I need to have it in my heart for part I if I want to really understand that inference. But feels like a bijection sort of thing. If these things are equal, then those things are equal. If the groups are equal, the fields are equal. Sounds very much like a bijection. And there's some stuff to count it and say, aha, it really is all of this stuff in the Galois group. So that is the Galois group of M over K, right? Oh, I suppose it's the Galois group of M over K if that's a Galois extension. Yeah, okay, so I shouldn't write Galois group M over K until I know that it's a Galois extension down here. In particular, it's that's Galois group of M over K if K is fixed, which would be the K is the, what's it, the image of K or whatever, is the things that are fixed in M by this automorphism group. Yeah, so this automorphism group might just fix everything in M. All the time there might not be any automorphisms. You've got to check any non-trivial automorphisms. If it's just the identity, then I think it's not a Galois extension. Yeah, something like that. Double check my definition of Galois. I know it's back at the start section 4, but I want to flip back and double check I've written down, that's from memory over there, the correct one of the 3 definitions of a Galois extension. Here it is. Yeah, so this automorphism thing up here, if that fixes exactly K, if that fix is exactly K, then you say that there's a Galois extension, and you write down that the Galois group is that. I really want to go back and understand at some point why the top one is Galois but not the bottom one. It's about normal and separable stuff, right? We talked at one point about how separable goes to both of them, but normal doesn't, I think. Yeah, okay, right. Every time when I flip around, I see these other things that I want to go back and understand. So it's really distracting. Okay, and I skimmed this at one point. I only find out how many fields just sort of makes sense because these things are finite. How many subgroups does it got? Good. Here is the minimal polynomial, and we saw this before. This is talking about the orbit. So your Galois group sends around some particular root alpha. Where does it go on the Galois group of L over K? Now, I'd really like to understand this because I'm trying to imagine the action of the Galois group on the roots, and partly I think, oh, isn't it just S5 or whatever, it just sends all the roots to everywhere. And that's not quite true. Things might have simpler minimal polynomials than that. There's a finite Galois extension. We can do better audio than that. Okay. Okay, so that's the minimal polynomial, that's the orbit of alpha, which doesn't have to be the whole thing, right? It doesn't have to be the whole thing. Imagine the cubic with real coefficients, 1 real root that's irrational and 2 complex roots. Then I think the Galois group just, so there's a transposition in the Galois group. I've got a feeling it's just S3, so there's an example somewhere around here, isn't there? Where's the example gone? Oh, here's an example. Here's a cubic. This one has got, this one I think has got 3 real roots to Desmos. We now have the stream technology to look at Desmos as well. So this one's got 3 real roots. Is this an example of one that's got 2 complex roots or 3 real roots? I think I can work it out actually. Oh no, I just want to apply it. And we've got the technology to show you Desmos too at the same time. So we can go Desmos, nice and large, and that cubic is in the notes that there's a section here talking about the cubic x cubed minus x minus 1/3. That's definitely got that many. Okay, and that's got 3 real roots. Okay, so that's not the sort that I was thinking about. There's a part of these notes coming up where we're going to look at. There's a part of these notes coming up where we're going to look at the discriminant in here, which is I think telling me whether this has got real roots or not. Okay, that one's got 3 real roots, and the Galois group down here. The reason I jumped to this example is that it turns out to have A3b as Galois group. So the orbit there, A3 is just cyclic. I'm trying to imagine if the orbit could be anything other than, everything, because the polynomial's irreducible, right? So the minimal polynomial. Well, let's find out. So look at the orbit, which might involve switching some stuff around. It must be the minimal polynomial of alpha over k. It's going to divide this thing, sure. We need to prove that p is irreducible. I'd like to know the degree of this. Okay, we're going to read. I haven't got section 5 yet, which is exactly what I said I was going to do section 5, but here we are. Getting better at section 4. Suppose for contradiction, p is not irreducible and it factorizes. Q and T are polynomials, and degrees both bigger than 1. Note that if hello, someone with a username that's a number. You found new media. You just type mathematics. Yeah. Just search mathematics and there's new stuff. I'm learning Galois theory. Thanks for the follow. Trying to understand the way that a particular group acts on the roots of a polynomial, because there's a link between the structure of the group and whether or not you can solve the polynomial with radicals. It's going to turn out that there are some quintics where the group is so rich and complicated that you can't solve the quintic with radicals. Right, okay. We were reading this. So suppose it factorizes and there's this Q. So gamma of Q, the action of this Galois group on the roots of Q, hang on. No. So we're looking at the action. So this is 0 because this is gamma of 0. So we're supposing that's a root of Q. But also Q has got coefficients in K, and gamma respects the K structure. It's a ring automorphism. So you can move it inside the polynomial. Polynomial's fine. It's still weird to me that polynomials work well with ring automorphisms, because I think a polynomial has been quite complicated and got a large set of things. So then in there, gamma of that's gamma of 0, which is 0. Wait, no, hang on. But that means that gamma of this is also 0. No. note that if Q of rho, which direction are we going here? If Q of rho is 0, then this thing is definitely gamma of 0. But also it's Q, yeah. So I would prefer it to present this, I think, in this order. To say, what's Q of gamma of rho? Where's gamma taking rho? Well, that's gamma of Q of rho, and rho was a root, so that's gamma of 0, which is 0. So this is taking gamma of rho to a root. That takes gamma takes rho to a root of Q. Okay, I'll present it in that order, I think. So the roots of Q are stable under the action. So gamma moves a root to a root. Now note that Q has a root in L since P splits in there, and P splits in L because it's the Galois extension. Q is a factor of P. Why does that mean Q's got any roots? Oh, P splits and Q's just going to have some of those roots in it. Okay, the set of roots of P of X contains a subset. Oh, right, okay. So the roots contains a subset, brackets, like roots of Q, which is stable under the Galois group and has cardinality strictly smaller than the degree of P of X, which is the orbit of, oh wait, hang on. Degree of P is the size of the orbit, because it's strictly smaller because this is a factor of the polynomial and it's stable, but that's supposed to be the orbit. Hang on. Orbit of alpha. Does it include alpha? No. The set of roots of P of X. Oh, the set of roots of P of X includes alpha because it's the roots up here. So some of the roots, if some of these roots are factorized, if some of these roots together gave a polynomial with coefficients in K, then the roots of that polynomial will be stable under P and include alpha. Well, no, okay, so maybe or maybe not, but that is it's supposed to be an orbit under the Galois group. You can't have part of your orbit being stable under the entire group. The point of the orbit is that you can get from anywhere in the orbit to anywhere else. So it's kind of synonymous in a way. So the thing I want to try and understand, this might not be quite true the way I say it, but the thing I'm going to have in my head is that the orbits of the roots under the Galois group action. Wow, there's a lot going on there. It's early in the morning for me. It's 20 past 9. I've got my coffee. The orbits of the roots under the actions of the Galois group, those orbits correspond to minimal polynomials for those roots. Now the Galois group, those polynomials are irreducible because the orbits are joined up. Reducing the polynomial will be a bit like reducing the orbit. So, okay. So my intuition that I've had for a while now this week has been that the Galois group kind of finds the different minimal polynomials. 2 seconds. I'm just going to sneeze. Excuse me. The Galois theory is so good it made me sneeze. My intuition here is that the Galois group is kind of playing with the different collections of roots corresponding to different minimal polynomials. which is weird. I kind of imagine the original polynomial to be the minimal polynomial, but that's not quite how it works. I can't really imagine it containing two different minimal polynomials though, because that sounds like it reduces. I think all of the roots should have the same minimal polynomial, right? If this thing is, oh, is P, is the original P irreducible or just separable? What's a Galois extension? Separable polynomial. Splitting field of a separable polynomial, but not necessarily a separable polynomial, but not necessarily an irreducible polynomial. So you could have these separate minimal polynomials around. That would still be a Galois extension, I think. Yeah. Okay. So there's a possibility here that the original polynomial that gave me my Galois extension when I moved to the splitting field was something like this. Something like this, x squared plus 1, x cubed minus 2. That's separable. It doesn't have repeated roots, but it's not irreducible. Right, okay, so if you have an irreducible polynomial, I know how to do a field extension with that. Here, if your polynomial if your polynomial is reducible, I think you can still do a Galois extension because this is you're good to go to the splitting field of the separable polynomial. And then some of these things behave, these roots are not really interchangeable. I think they're going to live in separate orbits. Does that make sense? So there'll be some subfields, so there'll be some group structure. That's my kind of big picture at the moment, I think. Which makes me think that irreducible polynomials are the ones where you get this nice enormous Galois group, and I've been struggling a little bit with the idea that the Galois group is not just permutations of all the roots. It's automorphisms, which need to preserve these field automorphisms need to preserve multiplication, which means that they preserve the respective minimal polynomials over the they preserve the respective minimal polynomials of these things. So if a root obeys a particular minimal polynomial, I think we've just found it, then the Galois group, the action of the Galois group is going to just orbit through. Yeah, okay. So this would pick up x minus I and x minus plus I for the kind of orbit for the minimal polynomial. Right, yeah, I know the minimal polynomial of I in that field extension is x squared plus 1, and this says that you can think of it as being something to do with the orbit. So, okay. The minimal polynomials are supposed to be irreducible, they're minimal. The original polynomial that I did my splitting field over might not be. Okay, not all polynomials are irreducible. I suppose if it reduces, then if my quintic reduces, then use separate parts for the. If it really factorizes into a quadratic and a cubic, then use the formulas on those. And that's going to be a case where the existence of an irreducible polynomial is the last thing that we do in these notes. We say, aha, there is an irreducible polynomial. Here's one. And it's got some complex roots. That's an important part of it, it seems, so that it's not A5. It's weird to me that this is in here somewhere, isn't it? Yeah, here. That the Galois group's not just Sn, not just permutations. It might only do even permutations if the discriminant is a positive square. Sorry, it is a square. which I'm going to think of as positive. Oh, I might just say positive. If I'm imagining k to be like the rationals or something, then this notation for the rationals, the set of non-zero squares in k is just the positive numbers. Oh, where's it gone? Down here. No. Down here. If k is the rationals, then k star squared is positive numbers. Positive rationals. Oh. No, that's not true, right? Because like 1/2 is not a square. Oh, you need the square root to be... Oh, if the square root is rational. It's good doing this example. Made me think. For Kemp's Cube, these squares are things like 4 over 9. That's a square in the rationals. I realise minus 4 over 9 isn't, but also 2 over 9 isn't a square in the rationals. Oh, so sometimes you do kind of, we're going to maybe do a square root or something, and it returns something that's just in k, and then that's not, you're losing out there somewhere where you could have got... We're going to see the structure stuff later today, but I think it's going to be something like that square root doesn't really... There's a square root somewhere which doesn't really extend your field, because after you've done the square root, you hit a rational, and if you hit a rational number, then cool, that was already in our field, so it's not an extension. Maybe, which is a little bit of redundancy and says that you're in AN rather than SN. Half as many symmetries. We'll get there. We'll get there. Okay. Right. Yep, so this is now talking about the action. This phi here is the the action on the roots of P. It's got no repeated roots, it's separable. I kind of want for all of these, I think, no repeated roots, no repeated roots, no repeated roots. This bit is something to do with the repeated roots, maybe, because it could be 0. That's the discriminant down here. Product of squares of differences. Yeah, okay, so for a quadratic, this looks at whether your roots are separated by a real number, which would square to a positive thing, or whether they're separated by a purely imaginary number, which is square to a negative thing. For a cubic, it's something more complicated. Everything's more complicated for cubics. Okay. Good example. Got to remember this is not just positive. Not just positive. Actual squares. Okay. Why is there an exclamation mark here? This thing lies in K. So this thing's always kind of, in some sense, real, but we calculate it down here. Okay. Right. P of x is irreducible over K and has no repeated roots. Then the image is a transitive subgroup of Sn. It sounds like my ideas that I was just saying out loud about large kind of group. Just up here, remind me about transitive subgroups. Transitive, only one orbit. Okay, now we're getting there. Okay, this is the link then. I kind of got somewhere near out loud. If you're irreducible, so I was worried a little bit about reducible polynomials having separate orbits, but this says transitive subgroup of Sn, only one orbit of roots. We were just thinking about orbits of roots. Yeah, okay. Since P is irreducible, it is the minimal polynomial. And we already calculated it above. They've got the same degree now. So the thing before. Okay. So transitive subgroups. So is that all of them? I'm surprised that I should maybe go and think about group theory a little bit more. I don't want to get too distracted by group theory, but I should maybe go and think about how. What are the transitive subgroups of Sn? What's the move? Is it? What's it? Sn itself is transitive because anything could move anywhere. Something like. Right, so there's some small ones as well, like the subgroup of just cycling around could move any element anywhere. So there are some small subgroups. Could move anything anywhere. But not the one that corresponds to like just flipping these ones. Okay, so when I saw that cubic and I was thinking out loud about whether it could be the case that it just flipped these roots, the answer is no. If the cubic's irreducible, that cubic's irreducible, so roots can go anywhere. Okay, orbits of roots. But for an irreducible polynomial, it really could send any root anywhere. It's not obvious that it could. Once you've sent some root somewhere, might not be Sn itself. Sn is sort of the most transitive thing. Anything could go anywhere, and even if I tell you where a couple of things go, you can still make some choices about everything else freely. We had something about that, like size of the Galois group being the degree of the field extension, and I think we're in here somewhere to work out when we get to the structure, I suppose. Section 5 is all about structure. Well, yeah, there's some. No, it really is, I think. Okay, so these proofs are quite easy. Polymorphism. Yep, acts on those. There is an identity. Yep, good. And it's generated by those. I guess the identity really is the identity. Point 2. Transitive. Oh yeah, that was the thing we were just talking about. 3, we have this polynomial, and it's the coefficients. So on the one hand, it's this, but on the other hand, it's equal to all of this. These things are equal. So on the one hand, you can write it out with coefficients. On the other hand, the coefficients are symmetric functions of the roots. So we did some work, or we looked at some work in section 2 to talk about how there's a unique polynomial so that you can write something, anything to do with the roots, even this mess, in terms of the coefficients. So that's pretty good. Okay, and then we looked at then we look at lowercase delta, which is the product not of the squares of the difference of the roots, but just of the difference of the roots. It's a weird kind of idea. So if I have 3 roots like this, then it's going to look at the products of these 1 to 2, 1 to 3, 2 to 3. Weird, okay. And then because this is an expression like that, it's symmetric. Oh, up to sine when you apply the permutation like this. So gamma comes in and permutes the roots, and delta is a polynomial, so we can move the gamma inside. Gamma just permutes the roots, and then that thing because of how it's defined with I less than j, is a thing up to sign. Okay. Excuse me. Right, okay. Am I well enough to do this? Yes. Let's go. So then down here, this thing lies in K, if and only if the image of phi lies inside of AN. So what's going on here? Image of phi. So the image of these permutations, if that's in A, then this is always a plus. Why would I want that to always be a plus? Oh, because gamma fixes this. Awkward. Gamma doesn't quite fix this. Gamma only fixes K. Right, okay. That's the point of, right, okay, that's how they work. So this thing is in K if and only if the image lies inside of A. So if you only do even permutations, then hooray, this thing will be fixed. This combination of the roots will be fixed by gamma because gamma kind of behaves nicely on these polynomials, and also if it only stirs your roots in an even manner, then it'll always give you a 1 here. That'll be fixed. Right, gamma literally fixes the elements of K. This is the most we've seen that. We were uncertain yesterday whether gamma was supposed to fix K as a set or element wise. And here we're very much saying, no, minus that element, right out. Minus that element is definitely in K, K is a field. But we're saying, no. This thing is only in K. If it's fixed. Hang on, so it's clear to me if this thing is in AN, then it's going to be fixed, so it's in K. If it's in K, then it's fixed, so the sign has to be 1. Right, okay. We can infer something about that sign on the right-hand side. Okay, so you can look at that, not quite discriminant, and that's in K. And then, other than the thing about 0, big delta is just the square of this, because it's the product with all the terms squared. Look down here on the previous page, and we had big delta is this thing with a square up here. So if little delta lies in K, big delta lies in the squares in K. Okay, good stuff. Then there's an example where we calculate it for a particular cubic and it's 1. So we say, aha, the Galois group lies in A, in this case 3, because that's the degree, I guess. Degree 3. P of x irreducible, so it's the minimal polynomial. So Galois group has order at least 3, and it's in A3. Good. Okay. Theorem of the primitive element. I think it's rearranging, right? So that you can take something that's extended by 2 elements and do something really clever to write it as the tangent of 1 element. Now we're at section 5, and I'm going to take a breather. Back in 5 minutes to actually think about cyclotomic extensions, which is the other for today. Half an hour. Section 4. Feeling good. We got the fundamental theorem of Galois theory now. And we got some understanding about how the Galois group acts, orbits, the orbits, and it acts. There's only one orbit, and that is the minimal polynomial. Multiply together the kind of splitting field for all of these things. It really is the orbit if your polynomial was irreducible. Okay, just 5 minutes. Back in a mo. Screen's going to say back soon. hot drink. I just once said mathematician a machine for turning coffee into theorems, and I'm not making any theorems, but I'm trying to read other people's theorems, so hot drinks all the way. Okay, what have we got? We've got special extensions today, special classes of extensions. There are three that I would like to understand. Cyclotomic extensions, which is something to do with the roots of unity. Down here, loads of exclamation marks on this. And some large polynomial to do with which one's a coprime. Nth root's really nice for p prime. Oh my goodness, look at all this. So that was 5.1, cyclotomic extensions. I also understand comer extensions, which seem to be something to do with x to the n minus a. And so it's simple extensions, good, okay. And then, so after characters down here, which I remember being really stressful on Tuesday, all of that, good. Then, okay, so 5.1 cyclotomic, 5.2, 5.3. 5.3 we're relatively happy with the notion of a solvable group, I think. We haven't read the kind of subset stuff, but whatever. Subgroup structure stuff down here. So we get to these as the center, good times. Looking at length, fine, okay. So all this stuff about group theory in here. Then solvability by radicals is the thing I want to do. So radical. So it's going to go cyclotomic for roots of unity, comma for roots of A, and then solvability by radical. The extension is said to be radical. Let's just read this. If it's an extension like this, and there are natural numbers such that each one is like an nth root. So those look like something to do with Kummer extensions, right? Where you have x to the n is a for some a that's already in your field. So you extend with alpha 1, then you say, okay, alpha n2 is going to be to the n2, natural numbers. Okay, so you can sort of keep going. Kummer extensions are radical. Okay, well, we need to understand more what a Kummer extension is. Okay, those are the plan. These are the three kind of foothills of the Quintic. They're kind of three mountains on my map that I'd like to understand. Okay, radical extension, J, fine extension. Here's some theorem 0.518 is just straight away in here. Okay. 0.518 is the important thing. It is probably my main aim for today, to understand this. So I'm going to read it once now and not understand it. And then I'm going to go back and get better at, this is going to be my motivation for understanding cyclotomic extensions, Kummer extensions, and then the radical extension made of this string of roots. I want to see how much of that is in here. Right, let's try and tidy this up a little bit. It's got some sort of stressful exclamation marks and stuff. I'm just going to put a little line under here for where the theorem is. It's not quite drawing a box around it, but yeah, I think I do want a box around it actually. So, and I'm going to change, this is a bit daft, I'm going to change colour to grey. Theorem 5.18 seems really important to me. Partly because of its enormous proof. Okay. That marks the first grey box of the live stream. Oh, different shades of grey, what's happened there? Don't like that at all. Right, okay. Sports have really tidy notes. It's helpful for the mind, I think. Oh, I don't love the top corner of that rectangle. Never mind. Okay, no more drawing rectangles. More reading. Again, it's taking up the left side. Oh, well, never mind. If the Galois group is solvable, then there exists a finite extension. You can go further. Okay, further. If that group's solvable, then the final thing is solvable, and that's also a Galois extension. Okay. What am I imagining? Imagining like throwing in more roots or something. Of K extension. This is something about the roots of unity over the previous. No, of the degree. There's the size mu subscript degree. That's really weird. Yeah, I didn't spot this last time round. That's mu subscript a number. That tells me which roots of unity to throw in. In M. Okay. You put the kind of roots of unity. This feels like putting the roots of unity into M. Okay. M is generated by the images of L. Okay, the images of, fine, ignore that for now. But M is generated by L and these extra K, this extra K sort of structure with the roots of unity. And that's an extension throwing in the roots of unity. Okay. So there exists a finite extension. Okay, and it's going to be finite probably by Art and Slammer because that's the main thing we've got that proves that the things are finite Galois extensions. Generated by the images of L and those roots of unities. Now the extension M over this bit, so not L, but extension of M over that bit, is a composition of coherent extensions. Particular MOK is a radical extension. Right, okay, a composition of, you can do lots of these, you have to do several of these things. What's the point of going up to here? Why doesn't L do some of these things, right? So L over K is a finite Galois extension. So if I just take M to be L, then achieving this is easy because L did that. L was Galois. I suppose that wouldn't have the roots of unity in it as well. And maybe it's the converse that's exciting, to be honest. So the converse down here is that you can go the other way. If there's a finite extension L such that the composed extension is radical. So 4 there is very special. 4 has got it says this is a composition of coherent extension, a special sort of radical extension, because not all radical extensions are coherent extensions, but all coherent extensions are radical extensions. But then going the other way, it says that the composed extension is radical. If you just do radical if you can extend up such that the composed extension is radical, then the group is solvable. This is, in some language, this says pretty much, sort of, look at that Quintic. Oh my goodness, look at that Quintic. The extension, if you could do a formula, the extension would be radical, but the group would then be solvable. So you can't solve that Quintic. So it's B that I really care about for my quest for the Quintic, because we're going to point at the Quintic at some point. Point at the Quintic and say, A formula. That would be a radical extension. And Galois group's not solvable if your composed extension was radical. Yeah, this is a big extension up. Then group would be solvable. Okay. So this is about putting in these roots where that's the degree of L over K. Why would that be relevant? So I can't guess why that would be relevant though. The degree of L over K being the number down there. So if you extend up, this kind of says if you extend up with a radical extension, then you might as well do it with one that is made of current extensions. So one that does all that as well, sort of. Then your group's solvable, so then you might as well go and find this M that does all of these. So we'll maybe see this applied in the form of if there exists a finite extension of composed extension radical, then without restriction of generality, it does all of this stuff as well. Because the group is solvable, the group will be solvable, and then do all of this. Maybe all of this is obvious if the extension is radical. I need to understand radical extensions. There you go. Okay, so this is my motivation. There's this explicit link here between the group being solvable, this finite filtration of normal subgroups going down within the group. Then for L over K, then you can go up to M by throwing in this unity or something. The images coincide from 3.133, that's what that says, right? The images coincide, so it doesn't really matter. Okay. Quick look at what sort of stuff is in the proof so that we can see where we're going to use facts about Kummer extensions, radical extensions, and maybe cyclotomic extensions. This seems to be the first thing I need to learn about. Oh gosh, so in here, what can I see? Co-extension, okay, maps co-extension like this. Choose such a Galois extension and maps. Okay, fine. Here's a diagram of field extensions. You could put the roots of unity in, you could go up to L, or you could go up to this big field J, which is an extension, okay, of either. It includes all of those. Both of these are subfields of J somehow. Let P be the field generated by L and those. Okay, so the ones that are kind of subbit that's actually generated by these things. Actually generated. So there might be some other dimension stuff going on that's just unrelated. Good, okay. And we're still talking about J though. It's a Galois group of J over K. I'll note the following three things. F1, P over K Galois extension. Ooh, surprising. It looks like the right hand's kind of bit of a substring of intermediate fields. Okay, anyway, the restriction map is injective. Okay, fine. Complicated stuff. We now prove A. Suppose that it's solvable by lemma 5.11, which was somewhere in, where was 5.11 going to be? 5.11 is somewhere in this thing about solvable groups and radical extensions and subgroups of things. So that the kind of subgroup here is solvable as well. So there's a finite filtration like this on P over K mu D. Fundamental theorem, Galois group theory. The subgroups correspond to a decreasing sequence of subfields. Right, so there we go. This is turning the subgroups, the normal subgroups, turning into subfields. such that this thing is a Galois extension. Fundamental theory says that, yeah, okay, each one, normal subgroups correspond to Galois extensions for, which is the top bit of the big field over the intermediate field, but also for the going down. Furthermore, those are the quotients, and those are. Wait, where's this cyclic? Why are those cyclic? Dilemma 5.15. Oh, so this is the fact about the cyclic 5.15. Which is, wow, these things have group is cyclic prime order. Finite solvable groups actually have cyclic quotients in for some, without loss of generality. You assume that you've taken a finite filtration where you split it down into these finite bits. You split your finite groups down. Okay, so in there somewhere is the kind of structure theorem or whatever. So those things are cyclic. Okay, this is the wow fact about cyclic quotients for finite solvable groups. The wow fact. Now note that. Okay. Lagrange's theorem. Oh my goodness. Right. Okay. So there's some group theory stuff in here. The polynomial. This thing splits in K mu D. We need to understand what those roots of unity are today. Theorem 5.7. 5.7 is supposed to 5.7 back here, which this claim somewhere in the middle of learning about Kimmerer extensions. So we'll get a theorem 5.7 somewhere in the middle of there. Let's quick look at 5.7. Really read this about what this is doing. Something about roots of unity. Okay, so we want to understand that as well then, so that we can get down here. This is a Kimmerer extension. Okay, so a particular radical extension. Right, so it's those cyclic quotients that mean that you get. This thing is the polynomial splits. The polynomial splits by this F3 fact up here. Okay, so it is a Kimmerer extension. So it's a radical extension. So theorem 5.7 seems to be important. It's going to be able to tell me that something is a Kimmerer extension, where this particular polynomial, this cyclotomic thing, splits. So particular is a radical extension. So that one is a radical extension. Yeah. So then this one down here is a radical extension as well, because it's generated by this root of unity. So that's a radical extension overall. So now set M equals P. Oh yeah, okay, choose it to be this one. Thus complete the proof of A. We will later set M equals P. So our aim is to prove that P has all of the properties that I think M in the statement is claimed to have. This is all proof of A. So big line to help me separate this out. And then B is the bit I really care about. I think. So this is fine. This is talking about including things in, and it turns out to be a radical extension. If you have a solvable group, that's nice. That tells me that you can solve something in a way. I think there's description of how to do that for a cubic after this theorem in the notes, which I might look at as well before lunch. But over here, it's the converse that's really exciting, which says something like, if you're trying to do a formula made of radical extensions, then your Galois group has to be solvable. That way around is the one I really care about. Quick skim, how bad is this? It goes down half a page like this. Okay, straight line please. Let's try and draw a line across this so that I can at a glance see where I am in the proof of B. Right down here, so this is going to try and prove that under here, if there exists a finite extension, the composed extension is radical. So suppose it's like this, where here is my radical extension. This is like the things that you build with your supposed formula for the quintic. In here, yeah, cool, that's just definition. That's all definition of radical extension. Definition of a radical extension. Sometimes my handwriting's so bad that I feel sorry for future me who will later try and read it. You know, you're going to be able to read your own handwriting, right? If no one else can. Here's the clever thing. The TB, product of those ends. Product of those ends. So you threw in some square roots and some cube roots, maybe. Let T be 6. Okay. As before, choose a Galois extension. Choose a big one, J, such that there are maps which include M for the thing that you just built and K. So choose some large J. I feel it reminds me a little bit of existence splitting fields or something. This idea that you can go up to a J if you have to, that includes kind of both. Not certain why that's allowed, but okay. Go up to this big space J. Fix maps of K extensions into J. Let E be the field actually generated by those in J. So all of this step here is just sort of setting up this field E that's generated by M and K. Okay, it's got some technicality to it that I don't fully appreciate, but choose a J extension, Galois extension. Oh, so J is a Galois extension. Are these E necessarily? It's something going to be something like choose a Galois extension and now prove that this is a Galois. Yeah, so this is going to turn out to be a Galois extension at some point. See from the definitions of E is, well, you had K like this and you added in these roots. It's generated by this stuff. And each one was in the previous sets. So each of the extensions is a Cumber extension, so more motivation for me to understand what Cumber extensions are. So Ni divides T. Wait, where was T? Oh, T's hiding in here. Take all the 6th roots of unity. Yeah, right, okay. Start by just having 6th roots of unity. Each of these is a Cumber extension since Ni divides T. Each of the extensions. Oh my goodness, so this statement is that this is a Galois extension over this thing. If you throw in an extra root, that's a that Galois extension is a Cumber extension because somehow Ni divides T. So it's sort of already that thing to the nth power. A Cumber extension is a particular thing that I want to understand today. Hence, so Galois group, open, how many brackets we got? Open. This thing over that thing. So Galois group of that, because this is a Cumber extension, Galois extension, is an abelian group by level 5.6. Here we go. So 5.6 seems important today. It's going to tell me that whenever you do a Quintic extension, you get an abelian group. On the other hand, the group over here is abelian by just 5.5, 5.2. So this sounds like easier stuff because this is sort of nothing to do with M. This is all the Quintic extension stuff. This is just something about root of unity. Applying theorem 4.4 again. Okay, this is the fundamental theorem, which we were reading yesterday. Conclude that this is solvable. E over K is solvable. We can do this. This is within reach, I think. Galois group of E over K is solvable by theorem 4.4. What is this telling me? Oh, solvable if and only if. Theorem 4.4 had something in there, right, about solvable? Looking at it just this morning. Theorem 4.4 had something about solvable? Has something about Galois extensions, right? The group. Oh, there's a Galois group there. If and only if. And over again, the small thing is a Galois extension, if and only if. That's a normal subgroup. The subgroup's abelian, so it's definitely normal. It's a really stupid observation, but I think it's what's one tiny element of what's going on in here. 3.4.4. That group is abelian, so that one is abelian. Overall, Galois groups of each of these things is an abelian group. Each time you added in a new one, you had an abelian group for the Galois group. So those subgroups. We've got an expression for M in terms of loads of stuff down here. Yeah, M is K of alpha 1 and alpha K. There's an expression here, so then K extended by having that. What was L? Why is L in that picture? Oh, M is an extension of L, so suppose that there is an extension of L that does this. Okay. So this thing's solvable. It's looking at the kind of Galois group is solvable because it has because it's abelian? No, because it's not abelian. This small thing is abelian. That thing is abelian. Overall, it's not necessarily abelian, but it is going to turn out to be solvable. LK is a quotient of the group thing and is thus solvable by lemma 5.11. You go down to a solvable groups down there. 5.11. 5.11. I thought we had stuff about solvable groups ages earlier. So it's 5.11 again. Oh, right. Normals and quotients are also solvable. That is going to turn out to be important. I shouldn't skip it. Okay, so there's something here about looking at your subgroups to be solvable. Once more, but fast. And this is our justification for spending the next 2.5 hours or something just learning about Quintic extensions and cyclotomic extensions and radical extensions. Once more, but fast. If the Galois group is solvable, then you can go up to something M where you throw in some roots of unity. There's a particular collection of roots of unity I would like you to throw in, which is then makes it into a radical extension. Those are kind of nice, I think. But more interestingly to me, for my quest, if you can extend up some finite extension such that this is now a radical extension, like something you built with formula involving radicals, then the Galois group is solvable because if it's radical, then the extensions, the Kimmer extensions, which have abelian quotients, just what you need to make the group solvable. And there's some stuff gluing it together along the way, but if it's a radical extension, thanks for the follow. If it's a radical extension, then the abelian a radical extension will just have nice simple abelian quotients, something like glue together solvable groups. That's my understanding of that. Thanks for the follow. Who's followed me? Facticals and System Shock. Thanks for the follows. So yeah, okay. Putting it all together. Never sure if I'm supposed to read out people's usernames. Some people really don't like it when I read out their username. I don't know if it's like not what we do here on Twitch or something. I think it's supposed to thank people when they follow. Anyway, it doesn't help that my eyesight's not good enough to read the username of the alert. In my defence, the alert is on a tiny preview screen for me. Okay. So, really want to understand. So this is A, this is B. Neater, please. Okay. Diagram of extensions. Okay. There's a lot of stuff going on in there, but I reckon we can do it. Back to 5. There's a link, right? We're going to see some abelian groups, and those are really simple, nice groups. That corresponds to the group structure of the Galois group being really simple and nice, but oh no, for the Quintic, that's going to be not the case. The Quintic has got awful, doesn't have this kind of nice structure. This is the main thing of Galois theory, really, that there's a link between the structure of the group and the roots of the polynomial, whether or not you can do a formula. Okay, so it's going to take me a little bit of time here, but I'm going to work quite slowly through how many pages of notes is this? 1 page, 2 page, 3 page, 4, 5, 6, and 7. 7.5. It's going to take me quite a while to work through 7.5 pages of notes. The thing to keep in mind is something I know about when they filmed Harry Potter. Let's try to find the quote. Harry Potter, I believe, was filmed at a rate of 1 page a day. I'm going to try and find a quote for that because I've said it a couple of times on the stream now per day. I know that's slowing down my rate. Harry Potter filming progress very slow. Oh, I can't find a citation for this at all. Yeah, no, okay. Only filmed 1 page per hour or day. Maybe if I Google the wrong thing, Google will be more helpful. No, now I've just found a headline that says Draco Malfoy is only in Harry Potter for a total of 31 minutes, which Here's a brilliant fact if true. Ah, right, okay. No more Harry Potter. Can't put it off anymore. We're going to have to learn chapter 5. Which we did skim read the other day, but now here we go. Okay, and there's a bit too much notes going on here. At most N, and then there's that star is I think. So this can go away. This can go away. So these are the nth roots of unity in E, and I immediately want to try and redefine that with K instead of E because he's using E for their field. Anyway. Those row in E, such that row to the end as well. Okay. Group structure, fine. The fields are lovely. They're called the nth roots of unity. What does that say? I don't know what that says. X minus x1. Try factoring it or something. Good, okay. Finite cyclic group. Good. Generated by any of its elements, right? Any of its elements are coprimes here. With coprime things. There's stuff here. It's an exercise to prove this. Surprising that it's a finite group. Oh, this is why I've tried writing the factorizing thing. You can't have that many roots, right? And cyclic because the clue here is to use cyclic if and only if there's at most one subgroup in G which has cardinality on G. So it's awkward because N might not be prime, so we're doing some careful stuff about divisors. And most one subgroup which has the cardinality size of G. Why does this clue that we've been given mention D again? Did he mean D? For any divisor there's a subgroup which has cardinality D. Yeah, I can't mention D again. Okay, don't love the clue. I know what a cyclic group is though. Why do I need a clue about a finite cyclic group? So this thing's commutative, definitely, sure, because no, why is it commutative? If you've got two, I mean, generally, if you've got two things that both get raised to 1, why is xy equal to yx? Well, this thing, like, why is xy equal to yx? Why is it commutative? Come on, James. Work it out. So if x and y So if you take elements x and y that both do this, it's a field. No, what's going on? What's going on? Why would those commute? It's being daft. I can't tell about this commute at all. I've got no ideas for how to check it either. Why would that possibly be true? What have I got? I could raise both to the power of n. Is that what we want? Not really. I could multiply both sides by x inverse. Is that good? Try and prove that those things are equal. Well, I suppose I know that this thing is in the set. Do I know it's equal to y? No. Chill. What are we doing? Okay, I'm gonna come back to it. One last chance to save myself. Is the field commutative? Is the field commutative? It is, isn't it? You're watching at home, shouting at the screen. All the rings are commutative in this. All the rings are commutative in this course. It includes the fields. Fields just commutative by definition. This is a very embarrassing live stream. Oh well. Way back on like page 1, it says everything's commutative in this course. Right. Why is it finite? A new and difficult challenge. There's not that many of them. A finite commutative group. So it might be cyclic. Is there an element of the correct order? So you take a prime divisor of n, please. These are integers. This is fine. Take a prime divisor. Now, yeah, no, okay, I'm not going to do this. I'm just embarrassing myself by slowly remembering things are commutative. I suppose upshot, right? I've remembered that things are commutative, so I get to take that with me. Even though I didn't prove the thing I was trying to prove, I remembered a thing that's going to be important all the time. Good. Okay. Through to unity. Anyway, okay. It is important that it's cyclic. I mean, that's just in the complex numbers. It's definitely cyclic, I guess. If E is the reals, then I just know what these things are. So, okay. I think in any sort of application to my Quintic over the rationals, I'm fine. I'm thinking about real roots of unity, which there aren't very many of. Anyway, maybe I'm imagining C for my field E. It's me imagining E to be equal to the complex numbers. In which case everything's nice. Good, okay. But maybe it's not the complex numbers, right? Because I'm going to add these in kind of one at a time, and the root's going to get added in not to the field C, but added into the field of stuff you'd calculated so far. So actually proving that that's a cyclic group is like proving that for this supposed Quintic formula that the group structure you get involves cyclic groups, involves abelian groups. Is part of the kind of big story. Okay, so I do need to do this proof at some point. Okay. If the number of them is n, we're going to call this. Okay, if the number of them is n, we're going to call an element primitive n through to its generator. If it's a generator, fine. Okay. And there you go for your cyclic group. Write the group law of G multiplicatively. Yep, okay, off you go. Send this to gamma to the A, where That is a group automorphism. So it's taking this. Now, is this an isomorphism from... Yeah, okay, so because it's cyclic, then you can take these powers. In you go. These things... K is the size of G. Cool, okay. So these things are at least different, which is good for your map I. Because these are different members generated by... Wait, what's gamma? Gamma's in G. Oh, but gamma might not generate G, right? Any G in this thing. This might not be prime. So this thing says something like... Yeah, I'm worried. For any A and Z, I have A mod K. Apply this to... this. So this is non-zero integers, but modded with kz, which is kind of what we're doing here. We're taking number a bar. I don't know why we're taking a and z. Shouldn't we be taking a in this thing, z, not kz star? I mean, if a is 0, this is sending everything to the identity, but hang on, that would be just I of 0 mod k. Yeah. Anyway, sending these things to powers of gamma. We can do this. So this is doable. What is this trying to say? So you give me a number on the side, like 3. That lives in Z, I guess 3 bar lives in Z mod kz star. And then I say, brilliant, here's an automorphism of groups. The automorphism is like this. I is going to send gamma to gamma cubed. Great, okay, you gave me a number, and I went, and what is that? Okay, so not gamma to the 3 bar. A has to be an integer. Gamma to the 3, gamma goes to gamma cubed is an isomorphism. Does that have to be co-prime to... No, okay, fine. So, I worry a bit about co-prime stuff in this, right? Isn't it true that if I send every element to... I was going to say every element to the power of the size of the group, but that's K, so that's like saying 0 sends everything to the identity, and I'm not supposed to work with 0 in here. So you send something that's not K, so not K, not 0 bar, don't be silly. Don't raise it to the power of the size of the group. Just cube stuff, if you like. I'm a bit surprised that's an isomorphism, even if K is 6 or something. So if K is 6, then I've got gamma. I've got my group looks like generator squared, cubed, 4, 5, and the identity. And then when I cube stuff, I get E, I get A cubed, I get A to the 6, which is the identity. I get A to the 9, which is A cubed. I get A to the 12, which is the identity, and I get A cubed, which is A cubed. Now this doesn't look like an isomorphism to me, to take a gamma in here and map it over there. That doesn't look like an isomorphism. Ooh, but no, this doesn't just mean non-zero. This means the units of Z mod Z. Yeah, not just with star, it means the units of Z mod KZ. Things that are inverse. So there, this star contains the information that it's supposed to be coprime. Coprime power, and then it's all fine. Okay. So that star means coprime. Okay. Coprime. Right, okay. I had a reservation that got cleared by noticing that this tiny star over here, that tiny star contains loads of information about taking a coprime, an integer that's coprime to k. Then you're okay, because 3 will have an inverse mod 5, so you could, the inverse of this map is to do gamma to the 3 inverse mod 5, or whatever mod k. That's the inverse of the map. So there's an isomorphism because you can undo it. Right, good. Oh, group theory. So much group theory. 2 hours. Done about 1/3 of a page. Okay. Suppose n is coprime to character of k. I only really care about character 0, so I'll just pretend this is true. Is that true? Yeah. No, I really do. Else splitting field this. Sometimes denote such a splitting field by mu n. L is only well defined up to isomorphism. It's got multiple roots. That doesn't have repeated roots. Fine, that's just what how repeated roots work. Thus, this thing, the size of that is n, and L over k is a Galois extension. Because this is a separable polynomial, and this is the splitting field for a separable polynomial. In particular, it's like this, by 5.1 just now. It's a cyclic group. Apparently, we see that there are this many primitive nth roots, generators of the cyclic group. That's the notation function. So, let this be the case. Is E the big field? No. Yeah, it really does weird me out that there's a K on the left and an E on the right. I think it might be a typo. Not all primitive. So this thing takes the product of all the kind of roots of primitive ones. And that looks like a kind of orbit kind of thing. Kind of orbit. Orbits. It's that big product over some stuff. Those are the roots. I'm hoping this turns out to be some sort of minimal polynomial for the extension or something. This root is 5n. Also note that, again, it's a simple extension because it's generated by any primitive n primitive unity. Yeah, okay. Polynomialing, that one depends only on n and k, not other stuff from the field. They're symmetric functions, permuted, so the coefficients are invariant. We've seen this sort of argument a couple of times. Polynomial only depends on n and k because all the splitting extensions are isomorphic by 3.13. 2. Normally we see 3 for the images being the same. Oh, those are isomorphic. The splitting extensions are isomorphic as 3.13.2. Excuse me. Okay. Right, where are we going with this? 5.4. Natural injection of groups into the isomorph. Oh my goodness. Automorphisms of groups of. What's this then? Natural injection of. So Galois groups to preserve K, and this is the automorphism as groups of just the roots of unity in L. permutations of the roots of unity. So your Galois group means everything, right? Including roots of whatever it's the splitting field for a separable polynomial. And then here we're saying that you could consider it Galois group just acts on L by ring automorphisms. Okay, so this is surjective if and only if. This is going to be something like you can get any possible automorphism of these from the Galois group. And then this, if and only if that's irreducible over K. That's a polynomial in K. Something about minimal polynomials. Okay, let omega be a primitive n3 unity. Why have we done that? We want to show that we can make any automorphism. Suppose that this polynomial is irreducible, so we're going that direction. So this annihilates omega because it's the those are obviously roots. It's split. It's kind of a product of linear terms. It must be the minimal polynomial of omega because it's irreducible. Hence this. A proposition of 3.9, which I can't remember. The degree of L over K. So 3.9 was that about counting degree? Minimal polynomial, natural isomorphism K extensions. Something next to A. Natural isomorphism K extensions over here. When you do your simple algebraic extension and you've got your minimal polynomial, there's a natural isomorphism of K extensions. K over P. Which then have degree L over K. Okay, back up. Oh, many pages. So the degree of the extension of all of L over K is at least as much as this. Because that's the minimal degree. That's the degree of the minimal polynomial. So the size of the Galois group. By 3.7, that's how big things are. Oh, no, so I need a different reason why this degree here. I need a different reason why that degree is bigger than or equal to phi of n. Is it the sort of simple thing that phi of n contains loads of degree within it by having, if that's the minimal polynomial for this root, then the kind of basis of polynomials up to that degree. Pi proposition 3.9. I'm going to go back to 3.9 again, do I? Simple extension, minimal polynomial, quotient is isomorphic to M. One more time. M is the simple extension of the isomorphism with K extensions where you quotient by the minimal polynomial, which is degree. Yeah, okay. So just the one where we extend with. Yeah, going all the way up to L. Right, okay, going all the way up to L might be different from just extending by putting in omega. So 3.9 says something like K of omega. That one has got degree 5n, where you do a simple extension by putting in omega. So the Galois group for L over K, which includes all of the roots of unity, might be bigger. That's how you count. That's the size. On the other hand, it's clearly less than or equal to phi of n by part I, where we injected it. We injected it into this automorphism as groups of phi and L, which is apparently not that large because the automorphisms of groups are the ones where you the automorphisms of that cyclic group are the ones where you raise elements to powers. You send an element to power doing the coprime thing that we were doing in 5.2. Was that all of the isomorphisms in 5.2? Yeah, well, no, okay. Oh, well, we said all of those are automorphisms. We just didn't say those are all of them, but we did say that, hey, there's quite a lot of them. No, there do need to be all of them for this to be the maximum, so that this injection is bounded. The size of this injection is bounded. I think it is all of them. Right, hence those things are equal. Conclude from I that it's surjective, that the size is just correct to match up. It's injective and the sizes are the same, so it's surjective. Okay. Now, the other way around. Suppose phi is surjective, hits all the automorphisms of that cyclic group, then the minimal polynomial is that by 5.2 and 4.6. 5.2 says here's what the isomorphisms are. If we're hitting all of them, we've got to know what they are. 4.6 was a while ago. 4.6, quick look, says down here, that's the minimal polynomial. It's the thing we saw before. Orbit of the thing we saw this morning. Orbit of over the roots. So it's orbiting over the roots. For the motion of the Galois, motion with the Galois group. And in here, later on, we were looking at in here, we discovered that was the minimal polynomial. One more time. We discovered the minimal polynomial really is that. Number 4.6. What does number 4.6 actually do? So it tells us that really is the minimal polynomial. Where you look at the thing over the orbit. How do I know it's the orbit? That's like 5.2. 5.2, I know where you go. So for these primitive ones, that's the orbit under automorphisms of any primitive root. You send a primitive root to another primitive root in order for that to be, so that you can undo it later. So if this Galois group goes into is surjective onto automorphisms, then that means that that injection is actually a surjection. That's bijection. Minimal polynomial. So 4.6 told us to find the thing by looking at the orbit, and in that case on the right, the orbit. Yeah, okay. I think we're basically there. The orbit means I've got to understand slightly better these automorphisms of the cyclic group. They're the ones where you send a primitive element to a primitive element, reminiscent of the polynomial stuff, right? Reminiscent of the ring homomorphism stuff. Because there's roots of polynomials sent to roots of polynomials. But not quite that, because these are primitive roots of unity. Okay. Got to send one of those to one of those. So the orbit is just over the primitive root, and then the 4.6 told me that that was the minimal polynomial. Okay, so it's irreducible. Okay. 5.5 looks really good because now we're talking about Q. So instead of K, we're talking about Q. This thing's irreducible has coefficients in Z. Not just Q, but in Z. Oh, content. Okay. It's all about content here. So we know it's irreducible if and only if the map is surjective. So I guess maybe we're trying to prove that this map from Galois group of extending up, so L over K. One more time, what's L? Getting lost with all the different letters and the way that some of them are going to turn out to be the same. Let L be a splitting field. L will be a splitting field for this polynomial. Okay. L will be a splitting field of this. Omega be a primitive nth root of unity. Splitting field for this. This polynomial in Q of x. So it's part of C. Let this be the minimal polynomial of omega over Q. And Qx divides xn minus 1. That's the polynomial t, such that you can multiply up to get x to the n minus 1. Note that t of x and q of x are monic because q, I guess by definition, is monic because it's the minimal polynomial, and then t is going to be monic as well, so that the coefficient matches up. So these things are both positive integers. Right, content is from the denominators here, so if you invert, then you'll get integers. Yeah, very good. On the other hand, compute that the content here is 1, so these product of contents is 1. So 1 over CT, 1 over CQ. We talked about this bit on Tuesday, I think, because we got interested in integers and Q appearing. That's also 1, and these are both integers, so they're both 1. So both of these polynomials have coefficients in Z, the constant's actually 1. So that 2.13 is the fact that C of TQ is equal to C of T, C of Q. The Gauss lemma, the content splits, but it's multiplicative. Now let P be a prime number, which is prime to n. What? What is going on in this sentence? Let P be a number that's prime to n? Do you want it prime to m or prime? Let now be a prime number P, which is prime to, oh gosh. I think probably just prime to n. Let now P be, I mean, oh, just comma which. Anyway, we claim that Q of this thing is 0. What are we trying to prove? This thing's irreducible. Suppose for contradiction this, then we have well, hang on, yeah, we know the product works like this, so t would be that, I think it would be a root of t of x to the p. Therefore, q of x would divide that. In other words, there is a polynomial. That's weird because q already divides this, and now it's going to divide t of x to the p. In other words, there is a polynomial h such that qx, hx, tx to the p. Note that h is also monic. Do the contents and run through product multiplicative rule again to see that h is also integer coefficients. Now notice that t of x to the p mod p is equal to t to the x, because the power function works nicely in fp. Gosh, so t's polynomial here, and this says that you can do each term one at a time, and oh crikey, p power function is additive in FP. Oh gosh, this says something like a plus b to the p is equal to a to the p plus b to the p in FP. Maybe I do care about finite fields, so that is good. P divides all of the binomial coefficients that are in between. So all the extra terms that I should write down here are all multiples of p, so they go away. So this t of x to the p says something like t of x to the p. Wait, just go over here. T of x to the power of p includes lots of terms like, that's polynomial raised to the power of p, but it's just, so each term to the power of p, and then each term to the power of p. Why am I not worried about the coefficient there? A to the p was a mod p. And we're doing a little bit of FLT as well, right? So I think the coefficients are maybe doing a to the p, a mod p, because a and p are coprime. Hooray for Fermat's Little theorem. Reducing mod p. We conclude that the greatest common divisor of q of x mod p and t of x mod p is not 1. Interesting. What's going on there? Because this thing is t of x to the power of p in the mod p world. So, and that's a unique factorization domain, I think. We're using factors u of d to conclude that this thing is just t of x to the power of p. So there's something like, not very much. These must be powers of t as well, I think. Is it a u of d? Good question. Something from Monday. Whereas trying to ignore finite fields. Let J be the greatest common divisor of that. Since these things work like that, and this is a factor, J squared would divide this. Oh, uh-oh. Repeated roots alert. Yep, it has repeated multiple roots, but it doesn't. Not even mod p. Non-zero. So, it's prime to n. And so, x to the n minus 1 mod p, greatest common divisor of these things is 1. Uh-oh, contradiction. Hooray. So q to the omega p is 0. Applying the claim for various prime numbers repeatedly, you see that this is true for any integer k coprime to n. In other words, all the primitive n through to unity are roots of q. Primitive ones, okay, are roots of q of x. Thus, the degree is bigger than or equal to phi of n. Finally, noted that by the definition, q divided the thing we started with, so which had degree phi of n, so qx must be equal to that polynomial. In particular, q of x, this thing, what a legend, is this big scary phi function. It's irreducible and has coefficients in z. Huh. What have I done then? Like 2 pages. I want to do 8. And I've got half an hour. So yeah, 2 hours. There we go. Hit 11:30. On track for 11:30. For 11 o'clock. To hit. I'm trying to track out my time here. Sorry. Just trying to hit 11:30 for radicals, and then 2 pages. I skip the 2 pages of this stuff. 12 o'clock here, rings and modules, loads of group stuff, and then we hit this at like 12:30 lunchtime. Okay, So I can get a little bit behind schedule, and that's fine. Cool. I think that adds up to a 5-minute break because I've run out of coffee. More coffee. Back in 5. Well, let's try and piece together. Sorry, before it goes out of my head, let's try and piece together what this says. So this is about roots of unity, and this polynomial where you just multiply together the primitive ones. Multiply together like the factors here of x minus omega for the primitive roots. Excuse me, primitive roots of unity. That thing turns out to have coefficients in z and be irreducible. I think I kind of want to do like an example for 4 or something. Things that are co-prime to 4 are 1 and 3, so over the roots of unity. Oh, this is pretty boring. Okay, there's a minimal polynomial. It's got coefficients in z. Maybe we should do 6 instead. Yeah, so for 6, the roots of unity in the complex plane lie around here, and phi nq means go up to the splitting field, yeah, which is part of C, and now find me the ones that are co-prime, which looks like 1. Ah, yeah, maybe we're supposed to throw in x minus 1 in there as well. Maybe. And that's reducible in Q. One's not a generator of that thing at all, is it? Because that's omega to the 0, and 0 is not co-prime, so I was not supposed to throw in 1. So non-1 numbers that are co-prime, or I guess consider this to be 0, 1, 2, 3, 5. Pick the ones that are co-prime to 6. The ones that are co-prime to 6 are 1 and 5. These ones are not co-prime, they're multiples of 2, that one's multiple of 3. If I do that, then whatever these are, I multiply those together and I'll get some irreducible polynomial with coefficients in z. Let's try it. That's where are these numbers? They're at sort of 60 degrees round, right? So 60 degrees round means that it's at 1 plus root 3 over 2 I. So I'm going to do x minus that and x plus x minus 1 minus root 3 over 2I. So this is the product of the primitive 6th roots of unity. And the claim is that this turns out to be a polynomial with coefficients in z, because, oh, that should be a half. When you add these roots together, you get 1, and when you multiply them together, you get a mess. No, you get 1/4 plus 3/4, which is 1. That is good. Let's double check that I've done that multiplication right with Wolfram Alpha or something. It's irreducible, it has coefficients in z, and the roots are the cube root of -1, which is what I wanted, and Wolfram Mathematics has given me some weird expression for the other one, but yeah, cube root of -1. Okay, good. So it has roots kind of with x to the 6 equals 1. Alpha to 6 is called roots. Not obvious from the quadratic, right? That's got information about the primitive roots of degree 6. Okay, time for another coffee break. If you're watching along at home, this is a chance to make a cup of coffee or tea or something. I'm going to be back in about 5 minutes on Twitch to talk about the next sort of extensions. Come on track. I've got timers now. Try and keep myself on track. See you back in 5 minutes. Hello. Oh, that thing happened where I went for a coffee break and came back with no idea what's going on. Good. Right. Okay. On this stream, we're about to understand cover extensions. While I had the kettle on, I was thinking a little bit about these roots of unity and why we're going to a lot of effort to think about the cases where n's not prime. And then I remembered that buried deep in that proof of 5.18, in about 4 pages' time, there's something where they take the product of loads of n's and look at the, I think the roots of unity of degree t. There's like a mu t. There's some mu t notation. We're going to skim and look at it. Over here, there's some, k of mu t notation in here, where t is the product of loads of stuff. So if you did, along the way of creating your Quintic formula, if you did lots of different sorts of square root and cube root, this takes the product of all the things you're planning to do, 2 and 3 in that example. And then that's not prime, because it's a big product. Further down here, we're looking at k and mu t, the roots of unity like that. And those are going to be something called a cover extension because ni divides t apparently. So something like we've chosen t to be just large enough that each one of these extensions counts as a cover extension. I don't know what that means. I'm going to find out. Something about the way that k of mu t is like the basic field in here, and then we're extending each time, one by one, each of the extensions. Okay, right, what do I want? I want to go back to find out what cover extensions are. So I skimmed this a couple of days ago, didn't make much headway with it. And now here we go. Once again, so it's going to be something about the field already contained all the roots of unity. So when I did this extension to this root, that was a root, because it was root of n, it was also going to be a root of this thing with the power of t in there. I've got my eyes shut, you can see the thing on the screen. Let me know if I'm getting close. Because t is going to be a big product of all these n's, so in particular, x to the t would be in my field because I know that x to the n is in my, by construction, the alpha to the n, the new thing that I'm extending with, the new thing satisfies alpha, that alpha I that we just saw in the proof somewhere, alpha I to the ni is going to be somewhere in there. So alpha I to the ni is in my field, so alpha I to the t is also going to be my field. And my field's already got the teeth roots of unity in it, so somehow that's relevant to it being a cover extension. It already had the teeth roots of unity in the field, and now I'm just throwing in a teeth root of some number that's in my field. That's apparently some class of cover extension, which we're going to find out about now. Right, good. What did I miss? Had my eyes shut? Nothing happened. Good. It'd be amazing if I open my eyes and oh no, the stream's just gone completely wrong. Everything's broken. Okay. So here's a claim here. Here's a claim here. Suppose the x to the n minus 1 splits in k. That means that you've already got the roots of that polynomial. So when I'm looking at k mu t, I'm saying, well, that thing has already got, in a few pages time, k mu t, this thing has already got the roots of unity of degree t, so x to the t already splits, I think. K mu t. And is that the right notation for extending mu t? Over here, I think we mentioned down here, abusing language, we're going to call it k mu n for the splitting field. Okay, so it's going to contain all of them. The splitting field might not have the degree. Yeah, the degree of the splitting field is something to do with the totient function of n. That's what we were doing around here. Okay, putting it all together. It's Thursday. Let's put this together. Right. Okay. So I've got to understand what a Kummer extension is now. Suppose you've already got the roots of unity. Already have roots of unity. It's already split. So k, we could already call k. K is kind of equal to k of mu n. It already contains those roots of unity. It kind of is the splitting. Oh, it contains a splitting field. Let's not go there. Okay. Let a be in k, and let m of k be a splitting extension for the polynomial. Right, okay, so now we're looking for roots of just some element in here. Later on we're going to say, oh, you were just doing a radical extension by throwing in powers of some element. If you already had the roots of unity, m over k is a splitting extension. Note that this thing, splitting extension for that polynomial. So separable, so this is a Galois extension over k. K already contained the roots of unity. So this thing's separable, so it's a splitting extension for a separable polynomial. That's a Galois extension. Such an extension is called a Kummer extension. The splitting extension for x of n. If you already had the roots of unity, now you might say, why? If I already had the roots of unity, can't I just multiply up, right? If you already had the cube root of -1, how are you going to get to the cube root of -2? Well, you just multiply by cube root of 2, right? Oh, that's an extension. Throwing in cube root of 2 is an extension. Because you can't make cube root of 2 by just doing stuff with this omega, right? You want cube root of 2 omega, but you can't make cube root of 2 omega by... Yeah, okay, that's an extension. Well, maybe you can, maybe you can't, but that's an extension. Maybe this thing already splits. If A is like 1 or something, then, right, well, that definitely already splits. If A is -1, then depending on n, that might already be a root. If n is, okay, if n is an even number, and you're saying, well, what about A equals -1? Well, that was already in k, because k, this thing splits in k, and -1's root. K, the splitting field is where you get all of the roots. Okay, so it might not be a new thing, but hey, in general, we'll be interested in cases where it is new stuff, throwing in the nth roots of A. Okay. So it's like throwing in nth roots of. So I should imagine it as throwing in the nth root, like the real nth root of A, and then multiplication will save the A and give me everything else. It's going to be a simple extension, right? Because it's just going to throw in one thing. I think I saw that somewhere down here. Such an extension is probably going to be simple. Okay. Lemma. Let rho be in M, or maybe L, such that rho to the n is A. So in this set, there's a unique group homomorphism. There's no L's on the page, so I really think they maybe mean M. Maybe mean M for the splitting extension. Such that, okay, you've now got, this is the splitting extension for this polynomial, so it's not surprising that you would have some things in there that we might want to talk about, which satisfy the polynomial. It splits, so find me the roots. There's a unique group homomorphism from the Galois group, which is going to permute things, m over k, to permute those I guess I don't know the degree of that extension, group homomorphism into mu nk, the cyclic group, such that you want me to go gamma of rho divided by rho so take your Galois group element take your Galois group element and find gamma of rho over rho. That gives you something in surprising. So this is the cyclic group. No, yeah. Does that just mean the cyclic group? Well, the notation mu n of k. It's like k of mu n means throw in the roots. Oh gosh, what's mu n of k? K of mu n means a field extension where you throw in the roots of unity into k. It's a little bit of an abuse of notation according to something over here because it's only specified up to isomorphism. But we're going to write k of mu n. I just saw mu n of k. What's mu n of k? It's up here, isn't it? Yeah, mu n of k. I wish it said k. Is a finite cyclic group, which is the roots of unity. They're actually in k. Okay. OE. So down here somewhere, group homomorphism from. So gamma group is going to be automorphisms of M over K. Those automorphisms should probably preserve polynomials in K, and I can see a polynomial in K. This one should preserve the roots of that, and a root of that should be a root. And we're going to map it into mu n of K, the cyclic group. Let's see how. I guess it's a group, and we're going to send it into a group such that phi of gamma. Right, give me an automorphism in the Galois group, and then this definition is going to tell me what to do with it in the cyclic group. It says, well, the cyclic group contains things like rho, the roots. I want you to work out gamma of rho. Where did the automorphism send that root? But then divide it by rho. So this automorphism was doing stuff like sending the cube root of 2. So I have these these roots, the cube root of 2 to the real one to cube root of 2 omega, some other cube root of 2. Other solutions to this. If I'm imagining sort of complex numbers and complex numbers extending over the rationals or something. Oh, I suppose this was already. K is not quite the rationals because I've already had to make this split, so I've already thrown in the roots of unity, and now I'm throwing in the roots of 2-nity. That's not what they're called. The roots of 2, which I'm going to call the roots of 2-nity. Roots of 2-nity. That's what we're studying now. Not the roots of unity anymore, the roots of 2-nity. And the automorphism is going to mix those around to send this thing here, maybe. And then there's some corresponding element of the cyclic group. So gamma is the thing that's moving around my roots of 2-nity, and I'm going to work out gamma of rho over rho, which would just be omega. I see, okay. So gamma sends 1. So in this example, gamma is sending this thing. Gamma so it's doing a lot of stirring on all of my roots of 2-nity. There are many roots of 2-nity. Nth roots of 2-nity? What am I calling these? There are many roots of 2-nity. Gamma's stirring all of them around. So it's sending this thing to this thing. And that corresponds to the way that I want this, what's this, map of, well, this is a map on the set of roots of unity, 1 going to omega, and also other things move around it as well. Other things move too. So that takes me from gamma an automorphism moving around the roots of tunity? 2, what is this on the right hand side? It's a rearrangement of the roots of unity. Is that what the cyclic group does? Can you think of the cyclic group as automorphisms of the... So the Galois group's not very interesting, it's just going to rotate, right? Because this group's cyclic. Small. I need to make a distinction, I think, between the roots of unity themselves. They form a group. This is a group action on that group, corresponding to multiplication by omega. So this says something like, your map's not that interesting, dude. Your map's not that interesting. It can only do an action from the cyclic group. It can only cycle the roots of tunity. So you thought you were all big coming in with your roots of A, and then your Galois group was going to permute them and do interesting things, but no, it's actually just going to do stuff from the cyclic group. Doesn't depend on the choice of row. Oh, okay, so if I choose my favourite row, I picked this one. 5 gamma, so 5 gamma is gamma of row. So for each gamma in the Galois group, show me, what is it doing to my favourite element? My favourite root of tunity. Favourite root of tunity. What's gamma doing? It's going to take that, it's taking that to, over here, it's taking that to omega. Right, it's got to take it to some of the, right, okay, it's not about permutations of the unity, it's about taking it to just one of the roots of unity, basically, up to divide by the one you chose. And doesn't depend on the one you chose. I've picked my favourite, but I could have picked a different one, and that's fine because all of them are kind of generated by multiples of the root of unity. Okay, right, here we go. Proof, down the bottom. It's going to be something like preservation of polynomials. There's the square, so this is the end of the proof down here. So I've got to understand this chunk of stuff that's above the line on the screen now. Okay, we compute that that thing where you're sending it to really was a root of unity, and because it's a gamma preserves the polynomial, it's all fine, yeah, okay. Indeed have that really is a root. To see the map does not depend on row, note that if you take a different one, row 1, sorry, the power of n, then row n, yeah. Thus there is an nth root of unity mu such that row 1 is just a multiple of this. So I could pick a different root of unity, but it's kind of just the same as the one, my favourite one, multiplied by some root of unity. Now, using the fact that this splits in k, you got all those roots of unity, you got all the roots of unity. We may compute this thing is mu. Mu on the top and bottom, and then that one moves inside gamma. Which I seem to have given an exclamation mark over here last time I looked at this. Mu is in K. Gamma respects the K structure. Gamma respects the K structure, which includes fixing K. And like multiples are nice, and so that mu is gamma of mu, and then multiplication is good, so you can bring it in. I understand that now. mu is in k. All of the roots of unity, because it's split. Okay, so this is where we've used the fact that k, the field we started with, already had the splitting, already had all the roots of unity, which means that this is nice. It wasn't some sort of like missing root of unity. We already had all of them. Your different choice was rho multiplied by an actual root of unity from k, and the gamma was supposed to preserve the k structure, including all the roots of unity. Supposed to fix the roots of unity. Fix the roots of unity? Yeah, they're in k. But you're fixing the roots of unity, there's not very much you can do. Up to multiplication here. The other ones are, yeah, okay, this is just saying the roots of unity are roots of unity, which we already had, multiplied by essentially cube root of 2. Okay, so the function finds independent row. Now we prove, it's going to be simple down here, called it. Prove that phi is a group homomorphism. Okay, I don't know what this diagram was supposed to be last time I was here. Multiplication of roots of unity. Okay, I kind of wish these were presented as fractions. I think that'd be easier to read. Now phi is a group homomorphism, so it's got to respect group action. It's got to respect a group thing about sticking these things together. For gamma and lambda in the Galois group, we have by definition that phi is supposed to be look at the composition map of rho divided by rho. This is like gamma lambda of rho over rho. That's just what phi does. And we know that phi of gamma and phi of lambda work like this. Gamma of rho over rho and lambda of rho over rho. And thus we have to prove that those things are equal, i.e. that gamma of lambda of rho is, there's like this extra factor of rho, lambda of rho, gamma of rho over rho. Right, but this splits in k, so we compute gamma of, the rho has gone inside the bracket, gamma of lambda of rho over rho is equal to, I'm just trying to make the maths larger, if anything, gamma lambda of rho over gamma of rho equals lambda of rho over rho. Right, what is going on here? Gamma of this. So rho, what was rho? Is rho an element of, rho's not an element of k, it's an element of the extended field. So it's not just that gamma fixes it. Oh, but gamma has a gamma top and bottom here. Gamma's just nice on division. And that thing on the top, gamma of lambda of rho. Lambda of rho. Lambda of rho is a root of unity, right? Because lambda sends things. No. No, it's not. Oh, but gamma of this thing? No, come on. Using the fact that that splits in k, so the roots of unity are already in there. Oh, but this thing, right, this thing is in k. This thing is in k, so it has to be over here. So now multiply up or something by gamma rho, and you get your bonus factor of rho downstairs. Multiply this up by rho and divide by, multiply this up by gamma of rho and divide by rho. Excellent stuff. Presented in a slightly funny order, and again, yeah, so it's about the argument here is a root of unity, and the fact that it splits means that that's in k. The Galois extension, Galois automorphism thing has to respect k, has to leave k fixed. If you've just joined us, we're thinking about Galois groups. This is where you throw in the roots of a polynomial to see what sort of structure you can make, and you look at structure on that by an operation that permutes around the new roots that you had, but it can't just do anything to the roots. It's got to respect multiplication is the key one. It's got to respect multiplication. so that the consequences of that are lots of stuff to do with minimal polynomials and lots of stuff to do with, oh, the roots have got to go to roots and not just any roots. There's consideration around about the orbits to do with maybe separate minimal polynomials. We've discovered the groups may be transitive if the polynomial is irreducible. Right now we're talking about the extension where you throw in the roots of some number. We're thinking about making a quintic formula. You can't, but we're thinking about making a quintic formula by throwing like fifth roots. If you throw in fifth roots of some number, so maybe you've got a complicated formula, you're just going to work out some stuff and then find the fifth roots of a number. We're talking about the way that those fifth roots thrown in will those fifth roots will give you a new field. If you already had the fifth roots of 1, then throwing in the fifth roots of 2 gives you just a simple extension. I'm trying to do that by showing that it's isomorphic, that the new Galois group you've got is not that interesting. It's isomorphic to the cyclic group. The new Galois group being isomorphic to a cyclic group means that it's abelian. We're going to see later that that abelian Galois group corresponds to an abelian quotient and lets us make a solvable group by talking about the normal subgroups with abelian quotients. And in particular, S5 is not abelian and doesn't have any other normal subgroups, so the only quotient it could have is itself, which is not abelian, so it's not going to be one of these. That's not the case that you can just get the roots of any quintic by throwing in fifth roots. We're getting closer. The language of the stuff that I'm saying out loud is getting closer and closer to the quintic of where I want to be. Stuff I'm saying out loud is supposed to be stuff that I'm trying to understand. This says essentially throwing in nth roots, because you're doing some sort of like nth root of an expression, gives you a really simple Galois extension, isomorphic to injected into a cyclic group, so abelian. Group homomorphism. There's some fun algebra going on here. Let's talk about how this extension, which is supposed to fix k, including the roots of unity, can't do that much more. You can cycle the roots of unity, but there's not that much else you can do. Okay. The map is clearly injective. Any element of the kernel of phi would fix all the roots of that, and hence would fix k. If you fix all the roots, let's understand that. Okay, so we understand this. We understand mathematics incrementally. We have to do very small steps. And here I'm mostly trying to understand this word hence right now for the next 2 or 3 minutes. Map's injective because any element of curve phi, the kernel would fix all the roots. The kernel of phi. Phi was the map up here which sent this into that cyclic group. I'm trying to show that the Galois group is nice and very small in a way. It's sort of just part of this cyclic group. So anything that sent that would fix all of the roots of unity. And because it's defined like this, what are you doing to the roots of tunity or something? Well, what's that got to do with fixing the roots of unity? So if you're in the kernel, that means you go to the identity map, which means that all of these things would be, oh I see, they'd be fixing all of rho. This would be the identity, which means that gamma of rho would be rho, which means precisely that it fixes all of the roots of x to the n minus a. Now what does it say? And hence would fix k, fix all the roots of x to the n minus a, hence would fix k. Now k includes just the roots of unity. Oh, it's the root. Those are the. If you fix all of those roots, wait, hang on. Any element of this is part of the. Any element of the kernel lives in here, right? Which is in the Galois group that fixes k. What are we checking? We're checking it's injective. We're checking it doesn't send two things to the same place. Oh yeah, no, I'm sorry. So this is checking that. So they're checking that injective. So to say that there's nothing interesting in the kernel. Anything in the kernel that fixes all of these would be not very interesting. Just going to fix all of. I think this should say M. Yeah, I think that should say M, because if you fix all of these, then you're fixing everything that generates M as well as K. Everything. You always fix K if you're in the Galois group. That's what Galois stuff's supposed to do. It's now going to fix. It's going to fix M. Yeah, and that's hard to do. If you fix M, the only thing in the Galois group that fixes M is the identity map. Right. Okay. I think I'm going to say that we kind of got there. Understanding is a slippery slope as well. You're going to keep pushing. I'm vaguely happy now, I think. Elements of the kernel fix all the roots, and so they fix everything in M, I think. That means, I think that... Yeah, I think that means it fixes everything in M, so it's... There's only one thing that does that, right? Fixes everything in M. So let's put a note here. Gamma row over row is the identity. We're calling that E or 1 or something. I'm going to call it 1. I think. I'll make that look more like a 1 so that I remember for the future. Good. Okay. Let's move on down to the bottom of this page. Proof also shows that there's a simple element extension generated by any root of that, because we know the cyclic group's generated by some of its elements, and then in here that Kummer extension is simple. Does that matter? Maybe. I'm not sure that's important. Okay, 5.6, big stuff, tells me that when I do a Kummer extension, so if you have the roots of unity going to the roots of something else, it's not that big. Not that big. You throw in an extension, you throw in one new element, basically, and then generate the rest by multiplication. And yeah, generated by any root of that. Okay, not that big, and that's the Galois group is cyclic. It can rotate around. Why is it not just the identity, right? Oh, because you get a kind of choice about which one. When you throw in cube root 2, you kind of, that thing could mean the one corresponding to here or here or here, and kind of those are all interchangeable. Excuse me. Those kind of things. It's odd. On my Argon diagram, I would really like to draw the roots of unity and the roots of trinity lining up, all nicely in the kind of lined up, but root of unity, the one that you add in, is kind of like an alien structure. It's kind of new and different. It doesn't have to exactly geometrically line up with your favourite root of unity. So that's weird. That says that if you have the roots of unity and then you move to ones with if you have the cube roots of 1 and you move to you also want the cube roots of 2, then so like the Galois group for, I guess these are different minimal polynomials, so these are different orbits. But it's sort of surprising to me that you can, the Galois group, which has got these roots that lie in this kind of nice, I drew it before and I'm drawing it again. I'm drawing it worse this time. The roots here lie in this kind of like double triangle. The corners of these two triangles. It's kind of interesting to me that the Galois group can rotate the inner triangle without rotating the outer triangle. It can do symmetries on each of them. Now, the question of which symmetries is still, I don't know, it's just the cyclic ones. Because that extension, so once you've extended to have the cube roots of 1, which is a cyclic extension by the cyclic group, the Galois group is cyclic, then you can extend to put these ones in as well. But I guess maybe surprisingly that's not trivial, but it is just a sort of cyclic. The extension, the Galois group is cyclic again, and the orbits there are separate because they have separate minimal polynomials. So a Galois group can come along and it can rotate this. Can't flip it. Automorphisms. It can't just keep one of the roots still. It's got to spin it. That is interesting. So your Galois group sees, I've drawn a triangle, but if it sees a polygon for the roots of A, it can only do things that are in the cyclic group. Can't do these reflections. Even though I can imagine like symmetries of the polygon, if I make a triangle and cut it out, I can imagine these will have reflection symmetries as well. It's insane that the Galois group doesn't do that, because there's a homomorphism into the cyclic group, and that is not one of the automorphisms of the cyclic group. That is very interesting. Cool, so your roots have this, in this case in that picture at the bottom, the roots have a nice structure, and the Galois group only does some symmetries on that. Okay, we're getting closer. We've discovered that Galois groups. Whenever I've heard the kind of first intro to this, like what's Galois theory, people will say something like, "Oh, it's about permutations of the roots, and then the group of those permutation actions has certain properties." And I've always imagined that really as like, oh, okay, so I imagine here are my scattered around roots, and we're just doing permutations of them. But actually, no, it's doing certain things on certain roots. It can't always jumble them. And even here we've got these roots of tunity around the outside. It's not just doing any symmetry of the triangle. There are kind of geometric symmetries I can imagine, but the Galois group's not doing that. And also I think there are cases where we saw for that cubic before, the three roots were just three kind of random real numbers, and Galois group doesn't care really that that's not triangle, that's not a very nice shape at all. It's doing some A3 stuff on that. It's doing rotations of those as well. That is a bit odd, really. The Galois group doesn't want to do these kind of reflections on the roots of unity because that's not a homomorphism. I should maybe dig in more to understand why it's not a homomorphism, but I think I'm falling a little bit behind schedule, and I want to keep going. For example, it says 11:30 over here, and it's 11:43 already, and I'm a page behind. It said 11 over here, didn't it? So I'm at roughly 1/3 speed of what I thought I would do an hour ago. Okay, we're going to read theorem 5.7. We're in good shape, I think, and we're understanding these kind of like, we're understanding what goes on when you have a formula and you're making the kind of Galois extension. Right. Okay, so this tells us three things. Suppose that x to the n minus 1 splits in k, this is the setup we have for a Galois extension. Suppose that L over k is a Galois extension, and that the Galois group is a cyclic group of order n. This is, okay, so they just said some sort of converse. We say this has got something to do with roots of unity. Okay. Oh, no, that's saying is a cyclic group of order n. Did this turn out to be surjective before? Sorry, I'm going back a page. Group homomorphism, group homomorphism. You don't know it's group isomorphism though, right? Anyway, injective, but not necessarily surjective onto all of the possible things you could do with a cyclic group. Interesting stuff. Okay. Suppose it's a Galois extension. Gal LK is a cyclic group of order n. Right. Choose a generator for that cyclic group. It's cyclic, so choose a generator. And let omega be, I prefer the word B here, I think, be a primitive nth root of unity in K. So I've got my sigma and I've got my omega. kind of think they're pretty similar, because sigma's generating a cyclic group and omega also generates a cyclic group. For any alpha in L, and then there's some massive calculation to do, beta of alpha. I wonder what that's going to be, but some huge combination involving some sigmas to find out where alpha's going, and then adding it up with omegas, because we know that the omegas exist in K, because we know that omegas exist in K because it splits. So we know these roots exist. Okay, so we can do this calculation in K, or we can do this calculation in L. It involves some stuff in L, sigma squared, sigma n minus 1. So taking a general thing where this thing was a cyclic group, this is going to be some construction which resembles the roots of A in some sense. Now, so here are the properties it's got. For any alpha in L, we have that this thing, raised to the power of n, is in K. So this thing is a kind of nth root in K. It could be lots of different things though. Beta of alpha, so my function here. Beta of alpha feels like it should be sort of different stuff for each alpha, right? It's doing some complicated calculation. So these nth powers are all in K, whatever you started with. If beta alpha is non-zero, okay, fine, maybe it could be 0, but fine, okay. If it's not 0, then L is K extended with beta. Okay, sure. So the big field L is kind of generated as the splitting field extension of this thing. I think there's lots of alphas. Oh, and there is such an alpha. Oh, right, okay. There is such an alpha such that this thing is non-zero. So you're going to have such an alpha in L, and when we don't need to think about all of them, we're just going to pick kind of one of them that does this. So looking for a generator, I think. There is an alpha in L such that this thing's non-zero, and then kind of generates this as an extension, L as an extension, K beta, where that's exactly a Kummer extension, because this is the splitting field where this thing would generate probably generate the other roots of this thing, xdn minus beta n, xdn minus beta n. So why do I have to do beta of alpha? Why can't I just look for, I suppose there's a method to find it. It's using the roots of unity. I mean, there's a complicated calculation here to check that it's actually in K, which involves this kind of nth power thing here. So, summary of what this theorem says. If you've already got the roots of unity in your field, and then you do a kind of Galois extension over it, which was pretty simple. I had a cyclic group for that Galois group of what, you did an extension, but not a very large one. So the Galois group of how it permutes these things is just cyclic, order n. Well, it's nice and simple. Then you could consider that to have been all you were really doing was adding the nth root of a particular number and consequences. So this is going to be a way to find such a number, so that you were adding the nth root of it by moving to the splitting field of the polynomial where that's an nth root. Do I want the n here? Maybe I don't want the n here. Oh, maybe I do. Yeah. We're going to find this element, beta minus alpha to the power of n, is going to be the number that we're finding nth roots of. Here it is. I mean, it's definitely a number. Once we've got it with that, it's definitely, here it is. And it's going to generate some stuff. So consequences. And we're going to show that it generates L. Okay. So we're going to find this number so that the nth power was already in K. So I can point at it and say, there, you were trying to find the nth root of that. You already had the nth power in k, and then you now look, beta is now in your field, in your large field, and it's generated by that. That's precisely what would happen if you set out to do the common extension, where you took in this extra. Yeah, we do mean this. Put in this extra thing that satisfied a particular equation, x to the n minus a. X to the n minus a is 0. The splitting field of that polynomial. Equals 0. B of alpha is non-zero, so this is splitting field of the extra roots of this. The roots of this include b and some other stuff. Okay, so this is a calculator, really. It's a calculator. There's one specific thing. It behaves like an nth root of something you already had. Okay. For the proof, we need something about characters of groups. Fun. Okay, so you're going to need something about cyclic groups. So your thing was a cyclic group before. Okay, I'm going to controversially try and skip 5.8 for time. Let's go. Let's see how much of the proof we can understand without 5.8. Let's go for theorem 5.7. Alpha in L, compute sigma of this. No, I don't know what sigma is. So straight faceplant straight away on my understanding. Oh, sigma. Sigma was, so part of this definition we have a sigma. Sigma is just some generator of this Galois group, which was cyclic. So sigma generator of the cyclic group. Sigma is a generator for the Galois group of L over K. So you come along and you apply sigma to this. Sigma fixes K. In particular, that means it fixes the roots of unity because we already had the roots of unity. And it behaves nicely under addition and multiplication, which means you can move sigmas in everywhere. And there were loads of powers of sigma in my definition of beta up there, including the fact that because that's a generator, sigma to the k or n or something is the identity. Identity map. N, cyclic group of order n up here. We already had the roots of unity, and then the next one up was a cyclic group of order n. So that splits. Okay. So this thing is nice and simple. You could recognize that this is just a multiple of b, because this kind of cyclic group is lovely. For a cyclic group, you multiply by sigma and you just get everything back again, but cycled around. Which is the same thing for beta by construction. That's omega to the n minus 1 of beta, which is because omega n is the root of unity, omega to the n is identity, so this is the inverse of omega. So sigma is just taking my beta thing here and giving me back not quite beta, but multiplied by some sort of root of unity. And you could keep doing this. You could keep rotating, and it would just keep spitting out a factor of 1 over this root of unity. So omega is just some root of unity at the top. Let omega be a primitive root of unity. Good. Okay. Okay. So as you start rotating, you see all of these. Right. I imagine there's some characters coming up now. Furthermore, oh no, we're still going. Furthermore, sigma of beta alpha of the n. Crikey, okay, nth power in there, but don't panic because sigma's really nice. Sigma behaves really well under that. Sigma's really nice. I'm a bit panicked because I'm worried about this power of n, but sigma's nice under multiplication. Sigma loves multiplication. Sigma is nice to multiplication. It's a Galois automorphism that respects the ring structure. So it's just this. Now that is the same thing as we knew what sigma was. It was doing this. And omega to the minus n is the identity because that's a root of unity. So what was this thing about doing it multiple times? Anyway, that's p alpha to the n. So sigma, oh look, sigma fixes it. So it's in k. That's what sigma does. Sigma only fixes things in k. Galois extension is really good. I'm really getting an understanding of what a Galois extension is. It feels stupid to say that 4 days into a quest to understand Galois theory, but when you read the definition, it's very much like, oh my goodness, the definition fix of the invariant group is this, and how can it not be? What does that mean? But now we're really getting there for, we're really using the fact that it fixes the elements of k. If you see something that it fixes, that's in k. If you see something in k, it fixes it. That equality in the definition of a Galois extension is very useful, as definitions always are. Okay, and then this bit defines a character. So down here, I'm going to go, don't understand it yet because I don't understand characters. But what's this going to do? It's going to make sure that there is such a thing where it's non-zero. And that we still need to generate the field. Let's read it from 5.8, the thing we were just doing. Yeah, from character theory, conclude that there is something where this is non-zero. Suppose that alpha is an L star, a non-zero element that does this, and that beta is non-zero from now on. Let alpha be beta to the n, since the omega inverse I beta are those things we just had, are all roots of x to the n minus 1. Yep, because you plug it in and you get something good. We've shown that x to the n minus a splits in L. We've got all these different roots. We've found roots. That's what you do when you want a splitting extension. We found these roots. Furthermore, we have shown above that that acts faithfully and transitively on the roots. Yeah, fine. Okay, we did some stuff in the Kummer extension section. Conclude from 4.6. This is irreducible. I've forgotten what 4.6 was. 4.6 was ages ago. Oh no! Back to 4.6 like yesterday, this morning, ages ago. 4.6 was a statement about minimal polynomials, where you look at the orbit. And that's going to be relevant now, isn't it? Good. I mean, because that's why I've gone back to it. Conclude that that is irreducible because it's the minimal polynomial, because this is the orbit. We already knew because it's a cyclic group, it acts transitively and faithfully on the roots. So this is going to be the orbit. Orbit means, so it's about the orbit, mumble, mumble, orbit, mumble, mumble, orbit, mumble, mumble, minimal polynomial. It's not equal at all, they're completely different things, but like the orbit is something to do with the minimal polynomial. You take in an orbit, and here we go, great. Hence that thing is n, and this is, yeah, okay. A note after proposition 3.9, quick look back to see if that was very insightful. Oh, right, okay, about splitting over it, about doing extension over a minimal polynomial and over an irreducible polynomial. No, what is this? That seems very vaguely important, but a star on it. We're doing an extension over a minimal polynomial here, and it turns out to be isomorphic to m. And there's this note about degree, which has a smiley face. I think I like this fact. Is what you want it to be if your polynomial was irreducible. Okay, back in to here. So I haven't understood characters yet, haven't read characters yet, but this note after proposition 3.9 is, this was saying that deg p, something to do with deg extension. L over k here, I suppose. So I've got kind of rough notes on what's going on. Theorem 3.17, I've forgotten what that is as well. Quick look back. 3.17 down here was just the size of the automorphism group being the degree. So on the left, that's something about polynomials. On the right, that's the degree. The degree of this is the size of the automorphism group, which is n. Okay, so these things are the same. one of them lies inside L or something. L is a split field. Okay, so some technicalities here to make sure that these things match up and that L really is generated by this. The only thing I haven't got is this character idea. So I'm moving the exclamation mark to just be here. There is such a beta that does this. Okay, I've got a choice now. I could go and understand more why there is some alpha, or I could pause and say, okay, fine, there is some like definition of characters in here. Doesn't look that hard. I'm now going to remove that one because I think it's mostly fine. This stuff up to here is the exclamation mark bit that I've skipped. Okay, quick look at it because that's good for me. It defines a new term as well. The characters. I can't immediately see what it's going to do with this. Group theory sort of thing. A character is a group homomorphism. H to E dice is already in the exclamation mark section, I think, for not something I understand right now. General result on characters of groups of values in multiplicative groups of fields. So a character is when you send a group homomorphism into the multiplicative group of a field. Of course you do. Distinct characters of E with H with values in E star. Take the values in E, take some values in E and suppose that this combination, I do want, redo please. I do want that to be 0. Okay, suppose that's 0 for all H in H. Then, well, it's not 0. Okay, so this says this kind of doesn't happen. The case that we've got where we've got this beta calculation up here, I guess I'm hoping that the something like the sigmas maybe, or maybe the omegas might be, maybe the sigmas are the characters, a group homomorphism. The sigmas are precisely, sigma is a generator of the Galois group, so it's definitely a map. Group homomorphism. Yeah, okay. We're always about group homomorphisms on this show. Always group homomorphisms. Good times. Yeah, okay. So I think the chi i's are going to be like the idea there. Distinct characters of H. Distinct homomorphisms from some group H. E star, and why have I got an H in there? I suppose it's always the case for all H in H. So what's the relationship here? Group homomorphism. So it's like, this is roughly, suppose that for all alpha, this beta calculation gave me 0. Well, then that only happens if all of the A coefficients are 0, and they're not, they are 1 omega squared. I think that's going to be the application of this theory, is where I want it, I suppose. Right, okay. Group homomorphisms. Can I understand these sigma of alphas as different group homomorphisms from H? Sigma squared? Can I understand alpha as a group homomorphism? I mean, is sigma of alpha to be a group homomorphism? Not really. Into E star into a field? Or maybe I'm supposed to be thinking about the omegas as a... No, for all H needs to line up with for all alpha, I think. Okay, well, let's have a look at the proof and then think about the application. Proofs by induction on the parameter K. Inclusion proposition clearly holds if K is 1. Excuse me. So if K is 1, then we've only got one term in here. So if that character was 0 for all H, that would say whenever you take a homomorphism H into E, if for all for all H in the group, the homomorphism always, multiplied by A1, you always get 0. That's suspicious. I think A1 is 0. Why can't the homomorphism just send everything to 0 for all H in the group? Is that homomorphism? Oh, it's supposed to go to E star. It's supposed to go to the multiplicative group. So these are not supposed to be 0. Not 0. Okay, here. E star. Once again, a tiny little star conveys loads of information. Okay. So Kai's not allowed to be 0, ever. So fine, okay. These characters go to non-zero numbers. So if somehow this was always 0, you would say, If just this first term was always 0, you'd say, probably A1 is the number 0 to make that happen. Okay. So now we're going to think about the harder case where we're doing induction. And we're going to think about the harder case where this thing vanishes for all H. So I've got maybe some combination of different homomorphisms. None of them are 0, but somehow the combination, whoops, is always 0. That's suspicious. Right, here we go. Are there distinct characters? If all the AI vanish, there is nothing to prove. Yeah, fine, okay. Assume at least one doesn't. Reorder, yeah. A2 is non-zero. Reorder so that A2 is non-zero. Fine, okay. Pick, what about A1? Oh, never mind. Pick alpha and E such that these characters disagree about where to send alpha. If they're always sending alpha, where the characters don't take values from E, they take values from H. If the characters always agree about where to send stuff, like they're not distinct. If we drop that, if they always agree, then we could have, if two of them agree, then we could have A1 be 3 and this one be minus 3, and oh no, it would still always be 0. And we'd have like secretly like this expression here would be like 3 chi1 minus 3 chi1, and then it's true. Whenever you put in H, these things return the same thing. So, oh no, it's gonna be 0 all the time, even though my coefficients aren't 0. If we know that, then we know if they're distinct. Then prove to me that chi1 and chi2 are different. That means choose some alpha in. I really think it should be in E, such that they're not the same. Then for any beta in E, we have, oh my goodness, right, come and show me, because this is a homomorphism from a group into the multiplicative group of the field, so non-zero. The multiplicative group of the field is quite a long way to say the field except 0, but hey. We have this thing, so you're summing, this is the sum of those things. Now, chi have to be multiplicative. Lots of things in this course through here we've been learning about things respecting multiplication. Here's another example of something that respects multiplication. Further down, and we can bring out chi1 of A. Oh, hang on, no. So you could just take chi1 of B, that expression, and multiply it. You could have just multiplied it by chi1 of alpha. So in here, okay, we're going to show that these things are distinct. So you had some combination, and I said, ooh, okay, maybe you plug in alpha beta, or maybe you plug in beta and then I multiply it by chi1 of alpha. Sneaky. Because those give very similar expressions that we can subtract one from the other. Clever idea. To get what is going on here. Something like these things. This sum is 0 and it's a smaller sum now. We've done some sort of elimination, which means that these things are all, these things are all 0. Contradiction. Yeah, okay, good. So you can do some clever kind of linear algebra thing. Almost linear algebra. I want to say linear algebra. That's a field. You do some field algebra to say, aha, I've made a smaller sum. So that's why we set it to be A2 non-zero, I think, not A1, because we're going to the plan was to cancel A1, cancel the A1 term out, to do two different expressions that were 0, two different expressions that were 0. This is supposed to be true for all H and H, so you could pick any beta and it would still be true that the combination of characters vanished. Okay, subtract, and then this is a thing with fewer terms in it. Can I understand that subtraction very quickly? 10 past 12. Race against time, really, on this quest. How much understanding can I pack into 1 week? Difference here, chi I minus chi 1. So all of these sums have got chi I in them, all of these ones have got chi 1 in them, because I just multiplied in this case rather than using the multiplicative rule. And the first term cancels. The first one will be x1 minus x1, which is 0, which is why the sum starts at 2 now. So we're going to look at these things. I've got A1. Have we used the fact that A2 is non-zero? I hope this is nothing to prove, right? An even smaller sum, right? I'm checking any division. I've missed a point here about why A2 non-zero matters. Okay, so we picked one such that chi 1 and chi 2 are non-zero. Oh, yeah. Right, so there's a contradiction at the end, because this thing, if these are different, looking at the A2 coefficient in particular is going to be our contradiction at the end, where we'll look at that and say, x2 alpha and x1 alpha are supposed to be different. That's why we're focusing in on 1 and 2. One of the thing we're using for subtraction to try and kill. 2, we're going to use that once we've done the subtraction. It's going to be the comparison moves to the A2 coefficient. We're assuming that was non-zero. I mean, if they're all 0, we're done. Okay, I'm taking off the exclamation mark. I think this is good. Combination of homomorphisms in your field. It's suspicious if it always sums to 0, and that's what we've got up here, right? Somehow. So now I want to clear this exclamation mark over here. Such that B of alpha. Note that any element of the Galois group defines a character on L star with values in L star. Any element of the Galois group defines a character means it's a homomorphism from L star? Yeah, okay, fine. From L star with values in L star, character on L star with values in L star. So these are both L star. Alpha is... Okay, so we're thinking of this as partly as a group. Think of it partly as a group and partly as a field. So we have this complicated statement down here about mapping from groups into a field, and hey, the non-zero elements for a field, they're both. That's a group and it's a anyway. So over here, when I saw these, sigma of alpha, sigma squared of alpha, these things are characters. They're homomorphisms from group non-zero elements. If I can think about non-zero alphas, think about non-zero alphas, which could have a star on it, I think. There's a non-zero alpha. Zero alpha obviously does this. Oh no, zero alpha obviously doesn't. Interesting, there is an alpha in L that does this, so that you plug in the alpha and you get homomorphism. Homomorphism because that's group automorphism, that's what the Galois group does. And if that sum was always 0, we would say, I'm going to come and do some subtraction and sort this out. And can't be always 0. Eventually I'll boil this down until I was looking at the coefficient and just say, oh, you've got like this last term here or something after doing all the elimination. Say, oh well, that's not always 0, so you're not allowed to send this always to 0. These maps are automorphisms, they don't send anything to 0. Okay, I'm going to clear this because I think we've now got some understanding of characters along the way. Woo! Right, okay. A little bit behind track, a little bit behind schedule, but I think I've now got more of an understanding of this thing. I'm going to read this bit one more time. So you have a non-zero alpha, which lets you generate this beta, and then beta really does generate as a field extension. This for the splitting extension really does generate this thing. Acts faithfully, and the degree, the dimension checks out. Okay, so L really is the splitting field. So that's the converse here to say, if you ever see a cyclic group as your Galois extension, then that's basically just a Cumber extension. And that's good news. It means that this quite complicated world of, here's the link, this quite complicated world of Galois groups and their normal subgroups and the structures there. Whenever you see a cyclic group, that just means Cumber extension. That's important because finite solvable groups only have cyclic quotients as their abelian quotients in the finite filtration. So many words. That's important because it means that we're going to be able to consider those as pretty much just Cumber extensions. Okay, and then there's beta. The strategy is that this combination with the roots of unity is how the cubic formula works in a way. It says, please go and calculate these, and I promise you they're not all 0. And thinking about the cube roots of that number or something. Okay, cubic formula application. If you've already got the cube roots of 1, then your next step up as a cyclic extension. Then okay, because your Galois group's not very big, so you're thinking about these symmetries. We already saw one where the Galois group was just S3, so that the Galois group there is an element you can calculate for that cubic we had before. Calculate this for any alpha. So there is some alpha out there where you can just carefully pick the alpha. There is some alpha out there where you can carefully pick the alpha, and that will give you this combination beta, which is then the cube roots of that which generate your extension. And that's pretty much what we're doing, right? So it's the beta cubed. In the cubic formula, there's this weird line where you write, consider this combination. That's basically, look at this number. Please find this number. I promise you, its cube is already in there. If n is 3, its cube is already in there. So just write down a cube root of this thing, right? Work it out and finally work it. Check it's non-zero, but then hey, work out a cube roots, and that will generate your roots. I'll generate enough of a field to be your roots. Can't quite tell you what your roots are in the field, can I? But you stand a chance now because you've generated something. Okay, getting closer to solving cubics, which is part of the game plan for the strategy here. Okay, accelerating a little bit. I'm going to go for a lunch break in about 10 minutes, but I want to skip through some stuff about solvable groups. We looked at this quite carefully on Tuesday, which is unusual for Tuesday, where we really brushed through a lot of stuff. The proof here about solvable groups gets an exclamation mark for now, because I understand that with my head what this says, but I do not understand the proof at all about these subgroups being solvable. It's about quotients, look, and these maps of quotients. It's maybe a little bit too hard for me right now. So all of this down to here. Solvable goes across. H is solvable and G. Yeah, all of this is a bit much. The structure of solvable groups. Finite groups supposed to end. This sort of group is always solvable. Now, let's see. What's this doing? How much do I understand this? Not much. Orbit stabilizer theorem. Cardinality pair of P, orbit of the unit element. That's cardinality 1, fixed point of the action, so it's equal to partition G. There must be an element such that this is not the fixed point of the action of G. By definition, G commutes with every element. So there's a normal subgroup is abelian and thus solvable. Furthermore, the quotient group is cardinality this, and by induction, work your way down so it's solvable. I think I do understand that in a way. It's solvable by choose some non-trivial element and then hope for the best and keep quotienting and induct. Oh yeah, quotient by the centre. The centre is non-trivial. Fixed point of the action. Do always partition G. Yeah, this is one of those counting arguments again. So there is something. This group's got a non-trivial center. Non-trivial center. So here's this kind of sketch. Non-trivial center. Quotient by that. Induct. Center is a normal subgroup. Yeah, and abelian. Quotient group has cardinality and so it's solvable. Yeah. Okay. So the length of the quantity like this. Lemma 5.15 is really important and gets a wow from me. No redundancies. Group is a cyclic group of prime order. It says finite solvable groups actually have just really boring cyclic quotients. We sort of know now that fundamental theorem of Galois theory that corresponds to those normal subgroups correspond to subfields, and the quotient is something to do with the Galois group over the intermediate subfield. If the Galois group there is cyclic, then it corresponds to a Kummer extension. You can kind of find something where it's the Kummer extension. I don't understand what the parallel of if you already had, if x to the n minus 1 already splits, if you already had the roots of unity. I don't quite see that parallel yet, but I think there's some stuff about throwing in all of the roots of unity coming up later on. If you throw the kitchen sink at it, make sure you've got all of those roots of unity. That k of mu t thing is coming up later on. Okay. So, structure theorem. It's not 12 o'clock at all, is it? And I'm skipping stuff. Structure theorem. Proper non-trivial subgroup. These are abelian, so split it down into its kind of. So to do with the structure theorem, to split down the abelian quotients. We looked at this in some detail on Tuesday. I think we were relieved to see a load of group theory after struggling through all the field extensions. Okay, I'm kind of happy with this, I think. Similar argument for not necessarily solvable finite groups, but non-zero finite groups. Okay. Really, I only care about S5. Here's an example. Abelian groups are solvable. Yep. Group S3 is solvable. Here you go. S5 is not solvable. Because A5 is a kind of roadblock here. It's simple and non-abelian. S5's got 120 elements and no normal subgroups. Simple, no non-trivial normal subgroups. Let me double check. Simple group really does mean mathematics, please. Non-trivial group. Only normal subgroups of the trivial. Yeah, no interesting normal subgroups. Okay. No non-trivial normal subgroups. Only normal, right? Only normal subgroups. Thanks, Wikipedia. Trivial group itself. Yeah, okay. No non-trivial normal subgroups. Okay. S5, important. There's the number 5. Quintic. We're getting close. Okay, final thing I need to understand before I can go to lunch. Having noted that I've skipped over all of the stuff about if you're solvable, then the subgroups are solvable and the quotient is solvable. Skipping all of the proof of 5.11 is kind of memorable enough that I feel like I can hold it in my head and it won't throw me later. And if I want to, I can come back and understand all the stuff about quotients. I can compartmentalize it, right? We are now in here for just, I think, 2 pages of radical extensions. Is this how far we want to go? Yeah, there's the big box that we're trying to get to, and an exclamation mark to clear. 5 minutes here. Okay, radical extension if it's like this, and there are natural numbers such that each time you were putting in roots of something you already had. Okay, Kummer extensions are radical, where for a Kummer extension, you kind of say you already had the roots of unity, and then you're doing this sort of thing. So with an extra restriction to say you already had the roots of unity. So not with all the roots. A Kummer extension say you already had the roots of unity. Then do this sort of thing. That's my understanding of Kummer extensions right now. So, yep, okay. And then over here, one exclamation mark to clear in this proof. And it's got at least 4 fields in it, so that's good, isn't it? 4 minutes on the clock. This question was really not supposed to be a race against time. It's a 40-hour job. Somehow every minute seems to count at times. L over K be a radical extension and J over L be a finite extension such that the common component extension is a Galois extension. Oh my goodness, I need a diagram. L over K radical, J over L finite. Not a very good diagram. And the composed extension J over K Galois. Okay. Then there is a field L prime. So there is a field L prime intermediate between J and L. L prime intermediate. I've got 3 minutes. L prime intermediate between J and L, such that this thing gets both best of both worlds. It's L prime over K exists L prime, such that there's a J over L and L prime is lovely. It's Galois and radical. So, oh goodness me. What a mess. You've been doing a radical extension and then you do a little bit more. You do a finite thing to get up to J. You're doing well. You're doing well with your radical extensions. And then you did some sort of weird finite extension over here that I don't totally understand, don't get it. But overall, you tell me, oh, it's fine, don't panic. The whole thing overall is a Galois extension. All my automorphisms for J still just fix K. So then there is an L prime somewhere in between. I'm going to be like, whoa, hold up. What are you doing with your big finite extension? Bring it back down to some L prime here, please. Which, keep it being Galois, but I want to do it radically. I want to do it with radical things on the way up. Radical, just throwing in roots of things. Giving me feelings about cyclic groups, Kummer extensions. Anyway, intermediate such that this is Galois and radical. Okay, and I've got to understand this chunk of text. And I've got 2 minutes on the clock. Oh, the time pressure is great fun. I'm surprised that this is what we've got. And there are natural numbers that work out like this. Yep, by assumption, that's what it meant for that one to be radical. L over K radical. We've used that here. Now let G be Galois group of J over K. It's finite, so it's generated. So J over K finite. I suppose this radical one is also finite because it's got finite things. So J over K is finite. So this Galois group is finite. It could just have as many as T things. Note that for any I in 1 up to K, and for any sigma in G, the Galois group. Okay, what do we have? What are we trying to do? We're applying sigma to those powers. Now sigma's nice to these powers, right? Alpha I to the ni, that's the identity. No, that's something in K. It's fixed by K. So this thing is going to be in, it's in the previous one. Sigma is nice to multiplication, and then sigma is also nice to alpha I, because alpha I was in, no, this thing with the nth power on it. Then sigma of, yeah, okay, so this thing was in the previous, in this set over here. This thing was in the set over here, so sigma of this thing to the nth power is in that, which is Kummer extension. So sigma of this Kummer extension, sigma of this radical extension means find out where you sent all of those. Find out where you sent all of those roots from before, and that's now the extension you've got because sigma's a nice automorphism. Find out where it sent them. Find out where it sent the generators. Where did sigma send the generators? Where did sigma send my generators? Did you see them? Where have they gone? There, that's where they've gone. So then this thing, the conclusion I suppose from this is that sigma alpha I to ni is in that radical extension. So sigma alpha I we can is a radical extension by putting in sigma alpha I to the ni. So clear the exclamation mark, I think, because I'm getting there. this thing is nth power is this thing to the nth power is in there. So as a radical extension, it just means putting in sigma of alpha I. I need to do that for all the alpha i's. So for each sigma in the Galois group, oh my goodness. So for each sigma, so this is kind of for all sigma for all I, or something around here. The nth powers were in the previous one, so just keep throwing in new. It's a radical extension with so many things in it, right? Sigma 1 of everything, sigma 2 of everything, sigma t of everything, all the way up. Oh my goodness. Which is then, that says orbit of alpha, because we've thought about where alpha goes under all of the sigmas. Under all sigma. So this K of the orbits is a radical extension now, because sigma of that, being very careful, sigma of that is sigma of this, and then the orbits are fixed. We see that this is, oh gosh, that's a Galois extension, it's closed. So set L prime to be that extension. So show me where my roots went under all elements of sigma in your new big Galois group. Whoa. You've made this huge J. Where do your automorphisms send my radical root things? Please generate that. Please generate that massive radical extension. If you do that, it's going to include loads of stuff. It's going to be, I claim, radical because that's how you built it, and it's going to be Galois because it only fixes K. Note before corollary 4.5. Backing up a little bit. Note before corollary 4.5. Note before. Oh yeah, okay. So for Galois, important characterization which we had this morning. ML intermediate field. It's a Galois extension if and only if all the maps have the same image. Yes, we're checking that the image of these maps is fixed. Galois groups are only supposed to fix the subfield. Yeah, okay. All the maps have the same image, which must be M. Important characterization of Galois extensions. M intermediate field. M over K is a Galois extension. This kind of intermediate field is a Galois extension over K, even only if the maps stay in there. All have the same image, all of M. And way back here on 10 pages later, we've shown that sigma on this set, because it's nice on the orbit, the generators here, it's a Galois extension. The image is always all of this. Images kind of coincide is what I want to write down here. Okay, I think I understand this a little bit. Good. L prime is nice. Yeah. Okay. Good. That's my understanding of this thing. We've reached the box. It's going to be time to understand the link between solvable groups. So this is planned for this afternoon's live stream. It's time to understand theorem 5.18. It's time to understand, we had a skim read of it this morning, but it's time to understand this link between throwing in all of the roots, throwing in a lot of roots of unity is enough for a solvable group. They do something with a solvable group, and conversely, the bit I really care about, if there's a finite extension such that the composed extension is radical, then the Galois group is solvable. This really says if you're doing a Quintic formula, then okay, so you do some sort of finite extension, fine. But you can compose it onto a radical because that's what you're doing with your roots, your nth roots. The Galois group is solvable, and S5 is not solvable. So I'm going to say that, aha, no, your Galois group might not be solvable. It is for small polynomials, you're fine. Aided by, we've spent all morning learning about roots of unity stuff, and we've got the proof here. We've skimmed it, and we've got an example coming up afterwards where we're going to apply it to cubic formulas. We kind of already know the cubic formula, but we're going to learn it again with Galois theory. That's the plan for this afternoon. So I've gone slightly over for the morning stream, but coming back at 1 p.m. quick lunch break, and then coming back at 1 p.m. I'm going to try and understand Great Big Theorem 5.18. Thanks for joining me on the quest. Quick look at the map, because that's where I like to go at the start and end of each live stream. I'm putting the stick figure pretty firmly over here. We've definitely been dealing with these foothills. So I'm going to put the little chap over here for the stuff we've been doing today. These camera extensions and radical extensions is where we are. And we're about to go and try and climb 5.18, but this time with understanding, once more with feeling, and then we'll be able to start saying stuff about cubics and quintics. Really hope that this afternoon I get to say vaguely intelligent things about a quintic, possibly with lots of backtracking. Right, cool, that's my afternoon. Thanks for watching, and I will see you for this afternoon's stream. But we're not done yet. The quest is to be continued.